Mexico in May 2023, joined by other countries. Quantum science and technology will be a key cross-cutting scientific field of the 21st century, having a tremendous impact on critical societal challenges highlighted by the United Nations 2030 Sustainable Development Goals, including climate, energy, food, safety, security, and clean water. The milestone of development of quantum science starts from the early 20th century with the invention of quanta and the photons. In the middle of 20th century, the development headed towards quantum electrodynamics and Bell's theorem. In the late 20th century, quantum computation and quantum cryptography emerged out from quantum science. Present state of quantum science and technology deals with quantum key distribution, quantum networks, quantum sensing, metrology, and many more. Because of the exponentially improved computer hardware, AI researchers were finally able to start building systems that could begin to approach human levels of intelligence. This breakthrough led to the rapid expansion of machine learning, a subset of AI that led to the development of many successful applications. Most is often cited as one of the key reasons why AI has seen such rapid progress in recent years. This trend will likely continue, leading to even more amazing advances in AI technology. In this direction, our 8 days faculty development program is aimed at understanding the application of quantum science and AI as quantum computing to address the challenges using artificial intelligence. Also, this 8 days faculty development program on emerging trends in quantum computing and AI for academia and research is aimed to mark the international year of quantum technology. The FTP is going to be remarkable as eminent resource person from national institutes like Indian Institute of Science, Bangalore, Council for Scientific Research, Scientific and Industrial Research, Hyderabad, National Institute of Engineering, Mysore, industries like IBM, quantum computing, and AI. The sessions of the FDP also span through the talks by the founders and co-founders of startup companies like Codecraft Academy and Discovery AI. Of course, any FDP is incomplete without diverse category of participants. Many academicians, researchers, and industry persons have joined for this FDP. Many faculty within Karnataka, other states of India have registered for this FDP. Participants are outside India also, are from outside India also. They are also perceiving the sessions of this FDP via YouTube live streaming. On behalf of the organizing team, I welcome all the dignitaries and participants, faculty, and student friends for the inauguration of this FDP. For today's inauguration, we have with us Dr. Srinivas T, Professor, Department of Electronics and Communication, IISc Bengaluru. He obtained his BSc Honours in Physics from New Science College, Hyderabad, and ME in Integrated and PhD from IISc. He was a postdoctoral research fellow at Toyohashi University of Technology, Japan during 1992 to 1996. His area of research interest is optical communication, in particular photonic integrated circuits. Sir has published about 150 research papers and guided 42 PhD students. He is a member of National Board of Accreditation, NBA. He was the chairman for Graduate Aptitude Test in Engineering for the IISc during 2010 to 2013. He is an active volunteer of IEEE Bangalore section and was the chair in 2024. Earlier, he was the chair of IEEE Photonic Society, IEEE Communication Society, Bangalore chapter. Welcome, sir, for this FDP. We have with us today Honorable actually Secretary, sir, was a busy schedule. He's unable to be present here. We have our beloved principal, Dr. B.G. Prasad, sir, and Dr. Ramesh Babu sir was supposed to be here, but all are busy with the academic works and so we have Ram Raju sir, Dr. Ram Raju sir, Vice Principal, Ranjan Sagar College of Engineering. We have HB EIE, Dr. Raj Shekhar sir, and we have Dr. Kiran Uttama, Professor, Department of ECE. We have Dr. Shobha Kerala, Dean IQAC, and Professor and Head of EC Department. And we have also with us today our HOD, CM Joseph, sir, Department of Physics. Dr. Smita Shashina, Head of the Department of Electronics and Telecommunication Engineering. I welcome you all. Now I request Dr. Preeti and Dr. Anita Suresh to escort chief guest and the dignitaries to the dais. Thank you, Dr. Preeti and Dr. Anita. To start in any holy occasion, it is our duty to remember the Almighty. Now I request the dignitaries on the dais to light the lamp. Let's all pray Almighty for the successful and effective completion of this every day. Thank you, sir. Thank you, madam. Now I request Dr. Priya Puskeri to present the invocation song. ಹದರಿನವಿಪೆ ಭಾವಿಸಿದವ ಹೇದಂಭ ನೀಡೊಲಿದು ನೀಡೆ ಮರಿಬರವ ಆರಂಭದಲ್ಲಿ ನಮಿಪೆ ಭಾವಿಸಿದವ ಆ ವಿರದ ವರದನೆ ನೀಡುತ್ತ ವಿರದ ವರದನ ಹಿಮೆ ಹರುಷದಿ ಕರಿ ಕರಜಿ ಹೆರಡ ಬರೆದು ಬರೆದು ತಂದು ನಂಬಿ ನಾಡಿಗಳು ಆರಂಭದಲ್ಲಿ ನಮಿವೆ ಭಾಗಿಸಿದವಾ ಆ सोमशापद विजित काम कामितदात वामदेवनतनुरिव नेमदि श्रीमन् श्यामसुन्दर स्वामी श्रीमन् श्यामसुन्दर नामते प्रेम ध्वनि ಕದಲಿ ನಮಿಪೆ ಬಾಗಿಸಿದವ ಹೇ ರಂಗ ನೀನೊಲಿದು ನೀಡೆಮಗೆ ವರ ನೀಡೆಮಗೆ ವರ ನೀಡೆ Thank you, Dr. Priya. Now I request Dr. Shobha Madam to welcome the dignitaries and chief guest. Very good morning to all the esteemed dignitaries on the dais, of the dais, respected faculty members, distinguished speakers who are here, as well as the participants. On behalf of Electronics and Communication Engineering, Electronics and Electrical Engineering, Electronics and Instrumentation Engineering, Electronics and Telecommunication Engineering, and Department of Physics, who are co-hosting this 8-day faculty development program on emerging trends in quantum computing and AI for academia and research. I would like to welcome all the participants as well as the dignitaries who are present here for this inaugural. So it is my absolute pleasure to extend my heartfelt gratitude to one and all for joining us in this knowledge enriching initiative. So I would like to start with a quote from Albert Einstein. Education is not the learning of facts, but the training of the mind to think. The moment we stop seeking new knowledge, we limit our potential. So lifelong learning is the way to stay relevant, adaptable, and truly alive in the world of constant change. So keeping this in mind, this faculty development program is a step towards unlocking the full potential to enhance the skill set, broaden our perspectives, and empower all of us in evolving academic as well as research landscape. In today's rapidly evolving technological landscape, quantum computing and artificial intelligence are at the forefront of groundbreaking advancements. These technologies are reshaping the way we approach computational problem solving and research across multiple disciplines. As educators and researchers, it is imperative that we stay ahead of these trends, explore their potential, and integrate them into our academia as well as research practices so that we will be ready for the next generation innovations. So this ability is designed to provide valuable insights into the latest development applications and challenges in these transformative fields. It will serve as the platform for knowledge sharing, collaborative learning, and discussions that will enhance our understanding and open the doors for future research and academic contributions. Events of this scale cannot be made possible without the unwavering support of our management. So I would like to start by sincerely thanking the management for their continuous encouragement and providing us the resources in order to conduct such impactful programs. So we have with us today as chief guest Dr. T. Srinivas for the inaugural function. He is also going to deliver a keynote address subsequently. So he is an internationally renowned expert in the domain of photonics and has significantly contributed towards the growth of research in his domain. He has also been the IEEE Bangalore section chair for the year 2024, and I am fortunate to be associated with him from the past 15 years. We have jointly done a lot of IEEE events together uh, under his guidance. So it is my privilege to welcome him to this program. I now request our principal, located chief guest. So we have with us our beloved principal, Dr. B.G. Prasad, who is the driving force behind the formulation and execution of such programs in emerging technology at our institute. I extend my warm welcome to our principal and I request the coordinators to give him a welcome bouquet.
We are very fortunate to have the guidance of our three vice principals, Dr. Ramesh Babu sir, Dr. Ramaraju sir, and Dr. Simha ma'am, who has been continuously guiding and supporting us in organizing such top-notch events. So on behalf of all the coordinating departments, I would like to extend my warm welcome to Dr. Raju sir in person and absentia to the other two vice principals. I would like to take this opportunity to welcome the deans, heads of the coordinating department, as well as the other department heads and faculty who have assembled here for this inaugural. Finally, a warm welcome to all the faculty members who have joined us today, the students and the participants who have joined us in this exciting learning experience. So, over the next 8 days, we will engage you in the thought provoking discussions and collaborative learning that will broaden your perspectives and contribute to the future of research and academic excellence. I encourage each one of you to actively participate, ask questions, and make the best use of the unique opportunity that is provided to you. So together, let us bridge the gap between the cutting edge technology and academia and pave way for innovative drive in education and research. Once again, I extend my warm welcome to one and all present here, and I wish this 8 day workshop will be highly enriching and an inspiring learning experience to all of us. Thank you. I request Dr. Madam Ma'am to welcome Dr. Shobha. I request Dr. Preeti to welcome Dr. Smita. Dr. Namrata, please welcome Dr. C.M. Joseph, sir. I request Dr. Meher ma'am to welcome Dr. Rajsekhar, sir, HOD EIA. Thank you, madam, for the delightful welcome. May I now request Chief Guest of our today's inaugural function, Dr. Srinivas, sir, to address the participants and students. Sir, please.
I'm very happy to be your college. I will thank Dr. Preeti for inviting me and also all the organizing team. So I would like to put two views in very short. First one, of course, most of the things are well described and known, but why only will it in a stage forward? So first point is why do we need to attend such activities? Is the first question. So most likely, and as an observation, you start with getting a participation certificate. That's the most important reason you attend to. And of course, and follow-ups of that. Like to show that to your principal or you want to present it during some NBA team and all that. That's fine. Then that is not that. And it's necessary sometimes. But let us dwell on more important reason that is being talked about. In the beginning, we said that this FDP will provide some in-depth knowledge, gaining all this. So I would like, I hope everyone focus on that part. So this is a subject, very emerging, lot of popular ones there. This many are interested, and more importantly, it's different from all the subjects that we have been studying. That's the most important difference. You cannot simply, in fact, I would like to say that you may not be able to learn from a lecture also. This is one of the subjects where you have to study yourself first and then listen to the lecture. Most of the lectures what I observe is up to a few to certain points catch. But after they will go over it, whatever you are expert. So I would suggest I hope all the experts will help you to give you enough resources to get you into the subject. I hope you're all very much interested to get into the subject first of all. Whatever area you're working in, you have seen, you're very multidisciplinary, whether you're in electronics or computer science or physics, anywhere will be here. There's a scope for this. In different directions. Of course, if you're a device oriented person, you can get into devices. If you're an organic person, you can get into those quantum algorithms and all. Okay, I hope it's fine. Please focus on the technical parts and learn. And of course, not only pre-learn, but also learn. Check out all this literature. There's very good literature now. Very popular subject. The technical part I learned more. So the second part I like very much in this program is you have involved many departments, in particular physics department. People consider photonics and this quantum are all physics, not related to electronics or computer science. When someone says photonics, they say that's physics. So we should give up that first of all. In fact, in the departments, in the institutions, we know that there are a lot of departments. Now you have department for almost every small, every new BTech program. Like you have BTech in AI and so department and so on. Originally, universities meant they have all of disciplines, like faculty of engineering, is simply one. Or if you look at IITs, for example, you have only electrical engineering department, nothing else, all of part of. So this implies that subjects are unified. Or you take a simple example of some VLSI. It was, of course, many of them have started with physics or mathematics. So it was mostly semiconductor solid state physicists who have done all this VLSI. And now we are taking it to the electronics ECE cloud. So please have a look at in the beginning, most of them were some fundamental things. Of course, a lot of practical developments, a lot of necessary and are there. But still, we cannot ignore physics or mathematics or other subjects also like chemistry as a first-year subjects. We should not consider them as a first-year subjects. In fact, I would suggest on because also the principal is here, we would like to say that in your center for excellence, I suppose you involve a few faculty from mathematics into AI or a few faculty from physics to this one and so on. Yeah. I suppose still after we had a response in IEEE to discuss about how to enhance our R&D and all that. That I cannot go into develop. Similar, it's very common for the Center for R&D also. Maybe I make a comment. The Center for R&D is purely for the technical benefit of faculty. That's the only fundamental reason why you should keep the skills or knowledge of the faculty at rest. That's all. Other things will follow later. Like you want to train the students, PLSI, or some other company will come and sponsor companies and set up some equipment. These are all next. Anyway, let's get that. I hope we'll involve more and more faculty from science into all this, particularly in the emerging areas like this. And of course, not de-emphasizing the application side, that will come and some other topics we will discuss. So thank you very much for listening to me, and I hope we'll have a nice time. And I congratulate the organizers for taking up this topic for this DP, and also I hope all of you will gain a lot of insight to the part of computing and quantum applications. Thank you.
Thank you very much, sir, for this insightful address to our participants and students. I hope surely they will make best use of the knowledge of the resource person. Thank you, sir. I now request our beloved principal, Dr. P.G. Prasad, sir, to motivate our participants with his blissful words. Please, sir.
Chief of the day, Satish Srinivas, Professor at Department of CAIS, you also the electrical section chair for 2024. I also know, sir, because we go on MBA visits 2, 3 visits. You're part of the same team. It's really an honor for you to have attended here and made your presence really honored by that. I welcome all the vice principals, studies, the organizing team, faculty members of the various departments, faculty from other colleges, my dear students. The FDP on emerging trends, quantum computing and AI for academic and research, really a apt topic today because this is shaping the next frontier in technology. A lot of new trends are taking place in both fields of quantum computing as well as AI. Already heard that the latest quantum computing based chips have come out, right? To the students. You heard of it? No. We should keep abreast of the technology that's happening. Which is that quantum chip? From the student side. You said yes. Microsoft has come out with, yeah? No. Mayana, right? That's the chip. We also have chips by, I think, Google, or below. Many more are on the card, and slowly we will see new research bringing out newer chips. That's why when Sir mentioned it's not just physics, it's not just any branch of engineering, it's a culmination of all the disciplines, major disciplines which make use of this quantum. It's a new way of computing, right? It's faster because of new materials used. So materials come in, your mechanical, your other branches also involved, electrical, electronics. So it's a gamut of all the engineering disciplines getting together to bring out new trends. And both the fields of AI and computing, quantum computing, we are seeing that it is applicable everywhere. It's like an omnipresent. So some of the emerging trends in quantum computing where you have practical applications like quantum supremacy, you have hybrid quantum classical systems, many approaches for blended classical, blending the classical computing with quantum techniques. So you have a lot of work happening in error correction and fault tolerance using quantum algorithms. The quantum hardware advancements, that's where the EC and chip manufacturing, new way of looking at development of hardware for carrying out this quantum comes in. Standardization, the quantum cloud computing, so that links to your science, networking and communications using quantum. All these are new trends in quantum computing, coupled with emerging trends in AI, where we talk of generative AI, explainable AI, federated learning, and so on and so forth. All these are new hybrid topics which are coming out, recent trends where both artificial intelligence as well as quantum computing are coming up. Now the topic here is putting together quantum computing and AI. So it's a blend, it's a synergy of the two. So then we talk of quantum machine learning, we talk of optimizing using quantum algorithms, and then handling huge data. That is more and more, let's say, optimized way and a faster way of doing it. So a growing interest where you apply quantum faster, it's more optimized. It has the potential to increase the speed of operations and improve the performance of. So these are some of the trends where both quantum computing and AI can sort of help in combine and the leverage that you get out of it, the researchers or the academia, in furthering your research, coming out with newer ways of looking at solving problems which are already there, but using quantum computation. Yeah. The topic is very apt. A lot of research is happening. I think you have a gamut of speakers who are lined up. It's general, rightly mentioned that we have a lot of top scientists and academicians who are delivering talks. To start off with, another is Professor T. Srinivas with his work in ISD, and he is also mentioning that we have to collaborate. I'd like to mention to Sir that we already have special interest groups to various departments. And, we have combination of people from different branches being part of us in various areas. And we are also looking at establishing center of excellence in this very block, subspace available, looking at putting up some center of excellence which is across, which will be used for all the faculties restricted to one department. With that, I would like to thank the organizers for having invited me and rightly chosen this topic, which is very apt for the day. Thank you very much and all the best.
Thank you very much, sir, for the informative and motivational words. I now request our Vice Principal, Dr. Ram Raju sir, to address the gathering.
Chino, science, it's for colleagues. First of all, I'd like to congratulate all the important taking initiative to the good talk. And the coordinates those have created the project. And I really sense there are good number of very good number of speakers. Definitely it will be. Only with the here a bit pains me. AP is not the person, the principal also to mention things because even the end of the importance. This is not the right to connect the FDP program. Because number one, all the high semester, even semester class, second, fourth, sixth, the class are going to zero. Valuation is going on. Then how can we get the fact that they are going to test their marks? How to value it? You know, so many things they're going to so many things that they are making with that evaluation. And since the students now just enter, the faculties are busy in taking the classes. Then we can easily send with all the quite important less number of at the same time, the management has really instructed and indicated in supporting this faculty development program for our internal faculty just in time for March. Because the same thing management incentives. So I hope that next time that but consider these things in the mind. Maybe at the of course there are problems in the institutions. You cannot know a specific time because sometimes one examination going on, other examination is started. Something like that. There are so many reasons are also there. We have to connect somehow connect the program possibly because as you know NBA land there is this certain program. It would happen like that. Anyway, and by seeing the very good speakers, that really sense that the faculty will attend the things effectively and see that the program you are going to enhance your knowledge. At the end, I have to share, take that. Yeah. But you know, the topic is very, very important. Artificial intelligence, machine learning, work wherever now, wherever you see any papers, AI enabled they come to know, say, you need to chat GPT, really, it worries a lot for us. Especially the non-computer branches like journalism, don't know where they can land. Because wherever you go, artificial intelligence is bringing down and go. We don't take the lead of the faculty that is really tourism, whether or not it's required there or not. They require knowledge because we have seen maybe 100 years there. I'm a huge of knowledge. What's the time report? I don't think you have sound. Also, ನಾವು ಹಸನು ನುಡಿಯಲ್ಲಿ ನಡೆಯಲ್ಲಿ ನೋಟದಲ್ಲಿ ಹೊಸರುತ್ತಿದೆ ಬಹಳ change the composition. It is going to happen because ಯಾವುದು ಕೂಡ ನಮ್ಮ ನಿಂತ್ಕೊಂಡು ನಿಂತ್ಕೊಳ್ಳೋದು because time changes. ಸೂರ್ಯ ಬರ್ತಾನೆ ಚಂದ್ರ ಬರ್ತಾನೆ. These things are going to happen without any news at all.
The technology is also immediately changing and it's coming like that. So many things are going to happen. But as the public, as the teacher in our duty to learn and finance or learn, consider the same is going to be possible to students. Hope that with these seminar, benefiting the faculty will benefit this. We shall. Thank you.
Thank you very much, sir. Surely we'll note all the points what you said, and we'll try to incorporate them in our next activity. Thank you very much. Now I request Dr. Anita ma'am to welcome Dr. Brain Kumar, sir, HOD Triple E Department. Request Dr. Anita ma'am to welcome Dr. Kiran Gupta. Ma'am. Thank you, Anita ma'am. Respected dignitaries, dear participants, faculty, research scholars, and my dear student friends, we have come to the end of today's inaugural function of 8 days FDP on emerging trends in quantum computing and AI for academia and research. To conclude the session, I request Dr. Raj Shekhar sir, Head Department of Electronics and Instrumentation Engineering, to deliver the vote of thanks.
Director Chemical Engineering and the department, Research Department. And sincere thanks to that Dr. Srinivas has taken this time to for our inauguration and session. Thank you very much. Now, here of the department, I sincere thanks to Dr. D.G. Prasad, Dr. Ramaraju, they are present in the annual functions. Also, all the participants and students, members in the department, all the heads of the department, and all are, thank you very much. Then after this session, again with the 3 days, again we are going to start the session. Thank you very much.
Thank you very much, sir, for the vote of thanks. I now request all the dignitaries and participants, faculty and student friends to kindly join for the Nada Dear participants, please note that after the inaugural session, there is one talk by keynote address by Dr. T. Srinivas. Now, kindly, I request all of you to join for the tea break.
ಇದೆಯಲ್ಲ
ಮುನ್ಸಬ್ ಸರ್ ಅಂತ ಈಗ
ಅವನಾ ಏ ಅವ್ನಿಗೆ ಹೇಳ್ಬೇಕಿತ್ತು ಫೋನ್ ಮಾಡ್ಬೇಕಿತ್ತು ಅವಾಗ ಹೇಳ್ತಿದ್ದೆ.
ಕನೆಕ್ಟ್ ಮಾಡಿದ್ದಾರೆ ಯಾಕಂತ ಗೊತ್ತಿದೆ
ಏ ಅದು ಪ್ರಾಬ್ಲಮ್ ಅಂತ ಅದು ಇಮೇಜ್ ನ ಅವರು ಇಲ್ಲಿ ಸ್ಟೇಟ್ ಬರ್ಬೇಕಾದ್ರೆ ಸೆಟ್ ಅವನು ಬ್ಲರ್ ಆಗಿದೆ ಇಲ್ಲೇ ಬ್ಲರ್ ಇದೆಯಲ್ಲ ಎಷ್ಟು ಎಡಿಟ್ ಆಗಿದೆ ಇಮೇಜ್ ನ ತಿಳಿಸಿಕೊಡ್ಬೇಕು ಅದು ಈ ಸೈಜ್ಗೆ ಸ್ಕ್ರೀನ್ ಸೈಜ್ ತಿಳ್ಕೊಬೇಕು ಅವರು ಅದೊಂದು ಅದು ಕಡಿಮೆ ಮಾಡಿದಾರಲ್ವಾ ಅದು ಚೆನ್ನಾಗಿ ರೆಸಲ್ಯೂಷನ್ ಮಾಡ್ಕೊಂಡ್ ಬರ್ಬೇಕು ಏನಿದೆ ಅದೇ ಬರ್ಬೇಕು ಇಲ್ಲ ಯಾರು ಅಂತ ಹೇಳಿದ್ರೆ ಈಗ ಬೇಡ So let us get started with the topic book, which make an overview and somewhat easy. Nowadays, it is called quantum information technology, which includes all aspects of communications, computing, measuring, sensing. There are many aspects of quantum uh, information technology. So the keyword is quantum. I just want to give you a description of the front, like front view like this. Anyway, still it's very, but you don't need to worry about what is there here. I just one or two points for me to take there itself. I'll take about 30 minutes or so, and then we'll have an opportunity again. So this is a list of the topics that I have put in these slides. They're very introductory. We start with the introduction to quantum. Then we'll see what are qubits. Then we'll distinguish what are qubits from classical qubits. And then we look at a few small systems like quantum logic gates. And then we see a few block diagrams of how a quantum computer looks like, and how quantum communication looks like. And we'll also see one of a protocol as an example for quantum key distribution. And then I'll put a little bit of photonics towards the end. So we'll try to get this. Thank you. So towards the end, we'll see a little bit of photonics. But throughout these slides, I'll use photons as the example of qubits to represent qubits. So qubits and quantum information has been used using many technologies like electronic states, NMR states, and so on and so forth. But it appears that photons are very practical compared to others. We'll verify this as we go along. So there are a lot of keywords as we are talking about. A lot of keywords are used in practice, and about 90% of the use that we see is fully. I mean, there are a lot of stuff inside, but it's a very generic nature. I would say. If you want to go more and more technical, we will technical. But these two important aspects of quantum. As was told in the beginning, this quantum is almost more than 100 years old. People have discovered or found out a new mechanism to understand things in a quantum way more than a century ago. Two aspects are generally used in practice. One is on the device level. You have a lot of quantum devices, like semiconductor devices, lasers, optical electronics, and so on. Then on the other side, in the recent times, you have information. Starting from the communication revolution, people have found how to represent information effectively. And they found that quantum is a very useful way to use it. But beyond that, not much has gone because of the lack of technology. Technology is an important driver in quantum information. Let's say we don't have a quantum computer now easily. Of course, in the beginning, in the introduction, we were talking about a few companies coming out with quantum chips. What was the main reason why we didn't have quantum? It is more than 30 years since people are talking about quantum information technology and quantum computers, but still we don't have practical. One of the most important things to say is the technology. We should compare this with the various technology that we have. The present day electronics has grown mainly because of this. Everything you have got of chip. Either the cell phones or laptop or TV, all of them have got a chip, which is doing all the functions necessary. Similar thing is not there for many technologies. Only at the beginning of the century, people have thought about MEMS. you can make mechanical components on chip. Similarly, we want technologies where we can make optical components on the chip. Then many of these will become, in particular, the quantum technology, quantum information technology will be realized through such on the chip technologies. So, so let us use the keyword quantum for now. We just use it as a very loose sense, not a very strict rigorous sense. Okay? We'll gradually develop the more fundamental properties. So we have distinguished quantum information technology, classical information. That is the opposite. Similarly, when you talk about a quantum computer, they say that a quantum computer is a what? Which makes use of quantum physics or the devices and the circuits involved will make use of quantum physics. Right. Similarly, quantum physics makes use of qubits for transferring information from one point to another. There are a lot of fighters in this we can discuss. For example, are we dealing with the classical information or quantum information, quantum communication? Those are things. This argument has come during the time of optical communication also. When people were talking about the fiber optic communications, people thought to transfer the classical information over an optical fiber, not purely optical information. For example, an image can be transferred from one point to the other directly. If it is a short distance, for example, you know that we can focus images from one point to another without processing. We will not debating such a thing with quantum also. So quantum communication link is the one which deals with either classical information or quantum information from a quantum point of view. In between, either the channel or the source or detector is maybe if you are talking about the classical information, it is to translate it into quantum information and then so that is a nuisance definition. You can refine gradually your thought process. So, so historically, Richard Feynman, the first one who said you can use quantum principles for computing. That is the crux of it. Many people have said about the use of quantum. Immediately people have realized that there are a lot of devices that can be made using quantum principles. But Richard Feynman is the one who said we can make computing using quantum. I suppose you have thought about it. See, we want to know, you see, this is before the current generation of classical computers. You know that there are a lot of all these high-speed computers now. They were not when he announced it. Of course, transmitter connects laser, some of those were invented by them. But people have not had high-speed computing as seen today. But in phenomenon along with some others also have foreseen that quantum principles will play an important role. In particular, Feynman has said that you can have quantum computing. Now, people call it quantum supervisory or quantum simulation. What to talk about quantum simulation follows his idea. But we also, if you there's a discussion, we can move to some discussion. Very interesting problem which doesn't exist in the classical physics. Okay. Oh, yes. The timeline. So the very timeline of development of quantum information, around 1980s, you can say, there's a lot of push because already quite an amount of information theory has developed by then. Then people thought why not we use quantum physics. One of the first protocols called BB84 protocol is one of the important first milestones in this direction. Then a lot of other things like building of a models for quantum computing, building of a model for quantum communication link, and all the problems. I will highlight one of the points. For example, sure SAGAR showed that the factoring large numbers is very easy. One of the big computational problems, say even computational problem, not necessarily from computer science point of view, was the number is very big. It's almost impossible to crack or uh, factorize. Nevertheless, it was uh, enormous scientific to someone calculate. And they said the order of complexity can drastically reduce if you use quantum physics. Another important algorithm that attracted attention was which showed that searching operation can be done very, very quickly. So there are many things like that. But let me jump to about 2016. That in the recent times, last 10 years, the big hype has been generated from this particular development in China. They have demonstrated a 1,200 kilometer QKD between China and Australia demonstrated. And all over the world, it generated a lot of trust in every government, in every almost all every accredited university has caught on to quantum uh, information. We have so much of interest in quantum information right now. The starting point is you can say earlier people were developing in India also. A lot of people have worked on quantum information, a lot of protocols, new theorems, and so on and so forth, and some demonstrations also. But this created a biggest impact. Then, of course, as you know, recently almost every big company is jumping into this quantum bandwagon. And morning, you have seen that Microsoft has a chip now. Similarly, Google, then IBM, Intel, and all those big companies are actually quantum well now. And people hope that in the near future, this will become more and more practical and important problems to be solved. There are a lot of popular books also that have come now, layman and without mathematics. A lot of interesting books are there. For example, uh, Michio Kaku's, I don't know someone has seen it. They show all that is possible. They will not give you the fundamentals, but they will show you what all that can be done. So let us get going and we will spend a little bit of time on the some basics or fundamental issues. We will look at it in a different way. Actually, we have to understand them in the right direction. See, we have said that we are going to replace bits with qubits in quantum information technology. And what does it mean is an important question. We said that quantum is an important keyword. So let us get into what is quantum. We have to start with a few objects. In the classical world, we use currents, voltages, light wave intensities, etc. to represent information. For example, 0 milliamperes, when it is 0 bit, and 1 milliampere when it is a bit, in the simplest sense. Or you can say horizontal polarization of a light wave will represent 0 bit, and vertical polarization will be spun. These are two examples. Similarly, there are many areas. You can use spin of an electron, angular momentum of a electron, and so on and so forth. There are many, many ways to, and nuclear states, people have been using all this. Okay, for in this today's discussion, we'll use photon particles. Now, we should replace the bulk objects with atomic or quantum particles, like electrons, photons, etc. Photon is one of the fundamental particles which has got very important quantum particles. We will not delve into all the mathematical aspects of that. We have described the operators. If you want to talk about quantum particles, you have to describe in terms of operators. So I would suggest, of course, it's not fully necessary, but even the electrical engineers will do well to look at little bit of quantum physics. Anyway, in today's discussion, we'll not go, we'll highlight only one. The quantum objects are characterized by quantum states. States, let us say, will not use always quantum. Classical objects, the states are well defined. Position of an object or the moment of an object is well defined. Suppose we say that an electron is at a particular position, then we know exactly where it is and what is the velocity and so on. The same argument doesn't apply to quantum objects. For example, if I have an electron or a proton at a particular point, it is only the probability that it is there at that point. Or if you are talking about the energy of the object, you can say energy is even the problem. So that means it's a random process. Random process means with respect to some variable like x, or suppose the electron is at a particular point x equals 0. You say that x from minus infinity to infinity anywhere it can be there. And the average of that is at x equal to 0. You are finding maximum probability at x equal to 0. You can imagine it, even though it may not be fully correct, imagine a Gaussian type of function with a peak at x equal to 0. And you always talk in terms of the moments or average. That is, I'm using some notation here. On the, during this course of this FDP, you will be getting more into the mathematical aspects of that. The ket notation. That notation, whatever you see, is called ket notation. Zero ket is the average probability of electron being at a particular point or object being at a particular point. Whatever physical parameter you are talking. Similarly, you use another state, ket 1, for two state 1. So you have qubit state 0 and state 1. Not well defined. They are random processes characterized by the PDFs, probability distribution functions. Okay? Little bit down physics. How do you get these PDFs? Is that the part of it? So the object properties should be described in some very good physical way. A lot of physical approaches are there in quantum. So one of them you can say is the Schrodinger watch. You have a Schrodinger equation. If you are given all the potential distributions and all the conditions, you can find out that wave function. Psi, whatever I am using here, can be called as a wave function. In fact, actually, the square of the wave function, according to quantum, square of the wave function is the probability distribution function. Okay. Similarly, there are other descriptions like Lagrangian formulation, density matrix formations, and so on and so forth. But for the time being, it is enough if we understand that they are not infinite. So how deal with qubits is an important question. So if you are given an object, what is the actual state of an object? Is it a 0 qubit state or 1 qubit state? That cannot be said exactly. It may be some arbitrary qubit state psi, which can be expressed as a linear combination of the 0 qubit state and 1 qubit state. You can say that 0 state and 1 state can be called as a basis for the actual state. And so you can see, because I have used indirectly a linear superposition of 0 ket and 1 ket. If you are talking about most of the phenomena, if you are using a phenomenon where linearity is applied, that's one of the most important principles that is used in describing the quantum processes. Let's assume for the time we are talking about a linear process. The linear superposition of 0 ket and 1 ket with alpha and beta being the coefficients. One of the important premise is that the wave function is complex. And so alpha and beta can be complex numbers. So it's a linear process of linear proportion of cubic states, complex projections, not real. So already first level we have got arbitrariness for the state of the object, unlike classical base. Okay, and then over and over we said that the superposition is complex. So what does it mean? In fact, we should dwell upon the real world. We feel that the real world is there. All the measurements that we are doing are all real measurements, like currents, voltages, distances, momentum, etc., etc. We feel that they are all real. The humanity has not come to grips with complex numbers, you can say, except we have convenience in electrical engineering. We use phase notation. Phase notation for describing our currents, voltages, and so on in electrical. That's why we use complex numbers. But is the real world complex? It's an important question. We say real world, we don't say complex world. We can simply say world that is real or not. That's an important point, more fundamental aspect. And I think it appears that the real world is really complex. Okay, that please think about it. So getting back to this, 0 1 ket and 1 ket can be represented by using matrices. You can say 0 1 column vector as 0 ket and 1 0 column vector as 1 ket. And so you know how to manipulate matrices. Okay. And you can also do oppositional operations once you have vectors or matrices. First step is you can change the coordinates. You can put in polar coordinates because if I talk about linears and polarization, is very convenient for me. Horizontal polarization can be 0 cubic state and vertical polarization can be in 1 cubic state and any arbitrary position of the photon can be resolved into their horizontal and vertical normals. You can also represent the state of the qubit on a sphere because only two variables are there. And the third variable taken as a point on the sphere and it's called a Plot sphere. The simple mathematical daily, not very so much difficult. Once you get to know that side is alpha and zero, you can see, construct a sphere or each side. That much of the property of the qubit. Now, if you want to get more and more qubits, what is important? You should have more and more objects, like two photons. If you have two photons, each of them have independent uh, qubit states and their PDF and joint PDF is the two qubit system. You can call it as 0 0 0 1 1 1 1 and then corresponding GTF, joint PDFs and their average values and so on. Of course, we need sometimes other moments also. I'm just using only first moment. Average value I'm using, not standard deviation numbers. They may be necessary longer. So we have four basic states. Like we have present by 0 0 0 You can also then call back point. 0 0 1 can be one basis. 0 0 1 0 0 1 0 0 and 1 0 0. You can choose many. There are a lot of options for basis states. Okay, all the linear algebra we know. You can take any basis, whichever is convenient. And of course, we know all the linear algebra properties that they should be orthogonal, all that. That will not use. But you can say that the actual state of a two qubit system psi is a linear combination of all these four bases. Vectors. So alpha 1, alpha 2, alpha 4 are the coefficients, complex coefficients, the square is equal to 1 and all that. And you can do transformations into different projections and so on. But of course, because there are four dimensions, It's almost impossible to represent graphically. There's no broad sphere like in multiple dimensions. Just before going further, if I have many, many qubit systems, like there are n objects, n qubits, then you have 2 power n basis states. So it is growing exponentially. The complexity is growing exponentially. That means if I want to build a 64 qubit quantum computer, that will be equal to 2 power 64 qubits. This 2 power 64 bit classical. That's a very crude way estimation. A lot of theories are there. If you get into current literature, you get more final quantum information. So I suppose you have to come to grips with the complexity of using the quantum. First important complexity that we noted is the states are indefinite and in complexity. And the second one is enormously, exponentially more and more information. So let us look at a few operations. And about two single qubit gates and qubit gates as well. So single qubit statements you do one qubit as the input and see what happens to it. Yeah. How to get that? What is the device or functionality of the black box? It is a different problem. Because we already know classical gates like NOT gate or any other such you can think of similar operations with qubits. I want a 0 qubit as the input and 1 qubit as the device. That can be said to be a quantum knot. But if you look at what happens, even mathematically, when you need to approach the problem mathematically, suppose you say 0 qubit with polygate, for example, one of the first one, x1, which is one of the poly x8, 0, 1 and 1, matrix representation, and you say that input is 0 qubit represented by 0, 1, and the buttons. So you can observe that this action is not. Similarly, others, for example, as an example, polynomial complex coefficient structures, that is a different point on the class here. Doesn't exist in classical sense. Let us jump to the Hallmark gates. H is a Hallmark gate operating at qubit state 0, and result is a linear combination of this. For example, you can say this here. For example, in terms of photons, you can say this is rotating. Is linear combination of states is possible. So this doesn't exist in classical sense. Which device does this? None will worry about it. So there are these are all significant topics. So there are symbols and representations. I'm showing you an example of gates. First is called the C naught gate. Let's see is the control port and T is the signal port, and a combination of T and C is in the different operations. So, taking a clue from the previous example, that's the last two columns, last two of the matrix 0, 1 and 1, 0. So, that means if you take the control port C as 0 qubit, you get a NOT operation. Right? Yeah. If the control port C is 1 qubit state, then it's a passport state. So the output is controlled by the C. That's right. Controlled. Similarly, you can have two different ports. Of course, you can build multi-port systems like this by defining matrices properly. Or the opposite way also, if you have a certain device which is functioning in a certain way, you can build a matrix first for it. So transform gauge, the operation is depending on C1 and C2 in such a way, and matrix where it doesn't fails. You can easily say, you see that I have constructed such that last four elements are 0 and 1 C1 and C2 are and various combinations can work out. There is good one. So a lot of analogs. You can build NAND gates, you can build fan of states. So we are yet going to take that's all. Then important points. So if you want to build a quantum information system, what are the various requirements and criteria? See, we are talking about these qubit states, which are not fixed. They can also change as we go. They are not very stable. You need to choose systems or qubit states which are relatively stable during the operation period. Okay, suppose you want to operate within a microsecond. So the states have to stay there for a microsecond. So such a problem. See, in fact, inherently, depending on system, they can simply change. This is called decoherence. Coherence is a property. Mathematically also to define. You have state S1, state S2. Correlation between them will define how stable they are. So if they are drastically different, we'll say that they are decoherent. Coherence is an important property of the qubit states. We should choose that. We should build system like. Similarly, we want very stable physical system. Should have many qubits easily. We should be able to generate. See, these are real problems that now I suppose people are from a device point of view or from a fundamental point of view. It's very difficult to build all these things, right? Then we should be able to initialize the states, even though we don't know what the states actually are. By passing through a certain gates, you can say this is the possibilities that are there. Similarly, we should be able to convert deterministically with some control. And also space dependence, not only time dependence, space dependence. If you are trying to transport from one point to the other point. As we know, many of the physical systems have got their own problems, like this one, and so on. So there are requirements that we will put in, and there are standards with all this criteria. Hmm? You see, suppose we initialize a set of qubits. What is the state that you get is not well defined. So you should have a certain states which you should be able to say that this can be used. These are the initial states. So the states of objects as they pass through certain systems. Earlier I have shown you some very simple gates. Suppose I pass through some beam splitter. What is the state that I get? So there can be, if you pass them through some complicated systems like an optical wave gate, then there are several possibilities. So you want only some small subset so that you can easily operate those systems. They should be very as simple as possible. See, this is like initializing. Yeah. There are many systems you want to start with some initial conditions. It's simple. So a lot of build models, simple are built. In fact, I would like to highlight this is not build a quantum some other quantum computer. You should think of these lines. This has happened during the development of our other systems also like our internet. You know, the 7-layer model. We use 7-layer model if you are talking about transmitting information from one computer, then from one place to another place. So it goes through several layers. Layer that goes through the design of quantum information systems also has become the practice. So they can be represented in block diagram form like that, and then reduced to all the quantum information operations systems of let us right. We'll highlight one of the important points in this slide. So in the design of which identify starting from the requirements. See, requirements comes towards the end, usually. This is what we want and how do we achieve that? Through all the different layers. We start with, see, we are just trying to compare. The scientists have tried to devise all this based on the existing models, but they are not sufficient. So you always start with the requirement, the function that you want, and then go back to the actual program that you like, algorithm that you like to us, and then divide it into some sets. One of the important points that we should identify here is space. You are getting quantum simulators. These are totally different from what we are thinking about conventional systems. Just as an example, like if you want to solve a differential equation. Suppose you are trying to solve a differential equation using classical methods. What we do like is you divide the matrix apart. You divide, you reduce, you discretize all the entire thing, and then convert to a matrix form, and then using a few fundamental linear operations, you arrive at a solution. Other approach that people have done during the beginning days of building of classical computers is analog computation. You look at phenomena where these differential equations are getting. For example, there is another equation for getting gravitation. You look at the physical phenomena, how gravity is getting what are solutions, and so on, and say this physical phenomenon is solving this mathematical problem. That means you are simulating a classical solution of a classical differential equation, as a solution of a differential equation by classical phenomena. Similarly, if you want to look at this quantum problem, suppose you want to not exactly quantum problem, you are trying to solve a differential equation by quantum means, you should look at a quantum phenomena. For example, you identify the energy states of an electron. And suppose you say that these are covered by the Schrödinger's equation. You're trying to solve the Schrödinger equation. That is a not equation, but the phenomena representing is a quantum. So you can call such an approach as the quantum simulation. Okay, this gradually boils down to what we have in the existing quantum simulators. That's what is the real meaning of quantum simulation. And this is the point where the supremacy of this quantum approach comes. Sometimes in many of these physical phenomena, like the energy states of an electron are very quick. They don't take so much time as the classical. Maybe they sometimes they take the same amount of time, but they're solving more complex mathematics. That is the advantage of using the quantum simulation or quantum also computational problems. So let us talk. I want to show you one or two specific cases. So we have already discussed many of this. I would also like because the physics department is supporting this, I would like to highlight the last point. See, the universe, electromagnetic waves or light waves is what we are using to observe the universe and find the properties in our life. An alternative way that is done in the physics is to grab the state of the universe, the darkness, dark matter, etc., have all been identified based on the gravitational approach. Because it is not matching with some observables. People said that let us assume that there's a matter which behaves differently, and they were able to explain the phenomena. So that's how people identified. Of course, a lot of changes are taking place because a lot of phenomena are very, very strange. In particular, maybe I will at the point later on. See, if I remember one important question, I'd like to pose. Even simplest one, like the gravity between the Earth and the Moon. There's a communication between the Earth and Moon to say that these two objects are existing here and are connected by gravity. This is not electromagnetic phenomenon. That they play a small role in terms of magnitude. But the Earth and Moon know that they are how do they know? That's where gravity is playing the role. So they are connected by gravity. Similarly, think of more complex problems. Long distance galaxies are interacting. Mhm. If there is change in one position of galaxy or some parameter, it is immediately sent to the other galaxy. If you look at electromagnetic waves, the speed of propagation, except don't match. The signal taking from one galaxy to the other galaxy will never reach. So there are a lot of important phenomena in the universe which can be truly said to be gravity. And this is an interesting part for those who want to learn mathematics. And on the top of this, an important discovery or recent development, you can say that gravity is also quantized. You have gravitational waves between these, not simply gravity. So please think about it. So let us go to one important case. So an important feature of quantum information or important interesting element is entanglement. You can generate objects, two photons, with correlated properties. That means if you know the property of one object, you can predict the properties of that object. This is like point. If I toss it 2 points, if I know the outcome of first point, I can predict what is the outcome of the second point. Classical effects, no, they are not correlated. Or you can imagine them recognize some string. Suppose I connect them by something, can rod and toss. One is head, other also the head of the electric. It is possible physically to create or generate objects, quantum objects with correlated properties. And they can be used. And you can also work out all the quantum states and the cubic states of these objects. You can simply say that they are a subset of the all possible combinations. And they can be used in many operations like in communications and so on. Maybe I would say that you can think of many of these. Actually, I did not start with that, but if we start with physical explanations, we have thought of a double slit experiment. As you know, quantum nature can be easily understood by using words called this double slit experiment or an interferometer. You can have an interferometer to say that path is taken by this qubit or this qubit and the linear operation of this is equal to and so on. So similarly, you can say that you can use a small example to check what happens to the state of the problem. So I'd like to describe one of the earliest protocols, which is very useful in QKD, quantum key distribution. Here, this is the thing. I would like to go a little bit fast because we cannot, I think we'll have close. So in the quantum communication world, they are called transmitter is called the Alice and the receiver is called the Bob. And there is a quantum channel which exchanges qubits between Alice and Bob. And the actual data is held by the conventional fiber optic cable, whatever, in the classical channel. And then he is a person who is trying to steal the information and trying to disturb it. That is the thing. And there are a lot of improvements on this. We have talked about until now qubits. That means there are two states, zero qubit states and one qubit state. You can have more than one state. It is possible. You can easily imagine that you can have many qubit states like multi-channel. So these are called qubits. That is called higher level slope. That's one of the recent activity that's going on around the world. And in our lab also we have a few developments that I'll show you later on. Then let me decide how this works, this BB84 protocol. I think during the course of your this workshop, you may have more detailed and more mathematical illustration on this. Okay. For the time being, let us just calculate the truth table or the comparison table, lookup table of this table. So you have a transmitter Alice with a qubits to send represented by the bulb indefinite state, but he has two choices. Alice has got two choices represented horizontal vertical basis or minus 45 plus 40 basis. Same heuristic can be represented by that. Heuristic is not known. The Alice can represent campaign. And in this protocol, the both Alice as well as Bob will choose a random way to choose. Maybe coins. You choose first basis of basis of line. Similarly, for example, I have given my earlier, yes. Suppose the input is a one state and Ali gives plus whatever it is, Bob uses horizontal vertical basis and receives a zero state, which is not a correct country in the report. So this one suppose you look at the second one, for example. Alice chooses the vertical horizontal basis to search one. Bob uses vertical horizontal to represent the two receive and you get one which is correct. You can see some other also. For example, 1, 2, 3, 4, 5, 6, 1 is also one state and plus minus whatever it is chosen by Alice and plus minus whatever is chosen by Bob. So that is also a valid state. There is one more, want to compare. Last but one is also one. So you can make all the combinations between Alice and Bob, sending different videos. Actually, it is not negative, I should keep on emphasizing. We are not actually looking at the cubic so you make a lookup table. And they exchange the lookup table has to be exchanged at the beginning before they start up application. This is only for the header information, only the bottom information. And what to observe that this protocol, Alice is choosing randomly the state, the basic state. Bob is also choosing randomly, independently. But lookup table is common. Lookup table they exchange. These are my entry is this, the out. My entry is this, the out. Etc. So what you observe is 50% of the entries are part in this protocol. Now, how does it improve the security? Is an important question. Let us assume that Eve is there in between, trying to steal the information. What she will do, she will know that this solar is in the 84 protocol. And then she will get four machines. Two machines for receiving, two machines for transmitting, and exactly point randomly she will choose basis and so on. Now calculate the extended table to all these elements. So what does the lookup table should contain? Lookup table, see the ball, I will say what doesn't that there is an even between. But once they compare the lookup table, exactly same these points, not use points. Okay, use points will be with us. They all separate there with us. Same table, if they compare, they will find only 25% of the patches elements. That means there is something wrong. Using similar approach, there are many protocols that we have a lot of variations and using different even device to make independent. Sometimes people call it some of these quantum operations device independent. They are independent of what device they choose. So a lot of things which are device dependent also. So I hope I have conveyed a little bit about how a BB81 protocol works. Crux of the problem is Alice and Bob are choosing the basis randomly with almost equal property. You can also make unequal property. 90% of the time, Alice will use first machine, first basis. Bob will use 90% of the time receiving. So you can calculate all problems. You have to add in addition to only tick marks, you should have is the probability. Then you can calculate what is the average probability of receiving the correct information, all that. Okay. So I'd like to show you a few pictures or a block diagrams of developers. So these are initial ones happened by Chinese and there are a lot more developers, the researchers. Yes, I would like to highlight one of the photonic spot. Some applications where photonic devices are used in this. Okay. So we go to this now goes okay. One of the important interesting developments is on the internet. People don't want communication only between a few points, 2 points. So one of the important problems in the traditional event of wireless networks right now is the number of users. Number of users have grown dramatically. That's how do we handle it? Is an important question why in the developments in 5G, 6G, and in IoT also, our major worry is how to handle so much of so many nodes, so many IP addresses. So people say that quantum approach is going to be very useful. Not exactly the sense of present quantum, present classical internet, but you can say subgroups within a house, for example, you know all these gadgets like in an IoT environment, each of them can be communicating by quantum. Whether brought the backbone in the classical, something like that. So a lot of developers people are working on taking different approaches, matrix approach, and so on and so forth, to exploit and explore how this quantum internet can work. It's very, very beginning stage. Let's look at the little bit of photonics. You can say photonics is the science and technology of using light waves, particles. Light has got both wave nature as well as particle nature to many, many applications. The most striking application, you know, is the fiber optic applications. You have long distance backbone links over all over the globe, and you have the national backbone network and a lot of usages and applications. So that shows this is stark different from traditional way of communication like satellite communications or the wireless communication that we have now, which is very popular and so on. Microwaves. So what is the most important plus point? The bandwidth. High bandwidth has been made possible just because of electronics. Even on the wireless, see, we use between cell phone and the tower between cell phones. It is a wireless connection, but the data will be difficult. At this moment, of course, we are able to see movies on cell phone, but just a few years ago, about 10 years or 5 years ago, so it was not possible to video connect it easily. So the new developments of 60 and so on are addressing these problems. In particular, number of users is important problem. So photonics appears to play an important role. So already, I mean, the next of the optical communication, people are talking about optical sensors in many, many ways, in many applications. You can have optical sensors are very, very sensitive compared to electronic sensors also. And into in some simple way or in bulky way, you can say, computing also is going on in optical domain. For example, image processing. If you want to do image process, if you want to identify the cancer image, then coherent techniques comparing different images has become very popular now. You can identify the patterns, all the points on the object can be correlated with all the points of the image using a very simple optical setup like a lens. Suppose you put a lens in between the object and the image plane, I mean, not just jet image, object plane and image plane, all the points of the object will be correlated with all the points of the image simultaneously. Or you can say Fourier transform. You can do Fourier transform very easily using optical lens. So these are the techniques that people are trying to do in optical computing. But what's the problem? We want we don't want a bulky system like an optical cable like this. We want a very on a chip. So that domain is called integrated photonics. You have to construct all these devices in a small way. That has taken a big way in optical engineering, say, what they call photonic circuits, optical integrated circuits. So photonics is going on. I'll show you a lot of examples done from our lab. This is one of the major activities in our lab. We've done since whenever a student we did optical modulators on a chip. You can do a high speed modulators, 5 Gbps or 2 Gbps very easily using electronic modulators. Similarly, in the recent times, there are a lot of activity on optical links. You can create mechanical as well as optical devices on a small silicon layer. That domain is called the optical links. So maybe I don't have to show you this. This is not a series of photonics, but a lot of developers are there. You can get into the connectivity to know what these developers. In fact, I would say, and there also, national programs are there. Almost every country has got a national program of finance. India also has got it, but in a very mild way still. Then many universities have advanced programs, at least at a research level and at slightly level, advanced level, they have advanced programs. In fact, many of you know that IIT Madras has got a tech in advance. IIT Delhi has got uh, fiber optics and microwave communications more than 30 years. They have it. Nice also we have about 26 faculty members interested in various aspects of science like biomedical applications, optical communication, devices, materials, and so on and so forth. I think we'll get those. This is particularly useful for those who want to do research and for those students who want to go for research in somewhere outside. Of course, India has certain limitations, facilities, and all the things. But I hope India will catch up soon. In fact, with this connection, I would say the important development is real estate for us. Because people consider the next stage of real estate once it's getting saturated. As you know, a lot of things are getting saturated in real estate. We have to do the investment, alternative approaches. People say silicon products is the next step in real estate. Yeah. So I would like to show how to. So a lot of things are getting done, but we'll try to go to the last one. I would like to show one of the devices which will appear in a quantum integrated circuits. So that's it. We'll quantum test. See, much of the silicon, real estate is on silicon. Much of real estate is on silicon, except for high speed devices in periphery. So this is also the way for us. We want active materials like in 3 for advanced. And already some crystals like lithium niobate are being grown on silicon. You can have silicon on insulator, that is one of the emerging products. And a lot of new little techniques are coming up, like Intel has been working on what's called computational lithography. Make an image and then project it on and on the wafer to create an actual circuit. It's a transformation thing. You don't have actual pattern. Yeah. You are straight. The image you will create. That's how we are trying to make more and more compact and more denser. We'll see some more example cycles, optical cycles. One more is we'll have to spend a minute on this. So how does a typical quantum communication device looks like? I just want to throw some examples of these cycles. You can see that the circular ones are very resilient. See the thin line, the black dark line can be called an optical line. They are very common traditionally integrated products. Okay. So these are like if you are been working with microwave circuits, they are almost equivalent to microwave waveguides. Okay. But of course, mathematics is slightly more complex because there's all dielectric waveguides. All these are on silicon and some of the universe, they are all dielectric waveguids. You also see a grading. So gradings are one of the very powerful devices in optics. They can act as filters. They can act as delays in many ways. You can also use, say, I mentioned an example where you can correlate with qubit space. You can also do these resonators and so on. There's a lot of applications. So we have some understanding of conventional photonic circuits like this. And in our lab, one of the activities that we do is to study these problems from a quantum point of view. For example, single photon wave, optical wave, what are the causes of spaces. And in particular, I would like to say that the modes of the object can be analogs of quantum states. Instead of using polarization or intensity, we can say that mode 1 will represent fluid state 0, mode 2 will represent fluid state 1, and so on. So some simple workout actually. Yeah, they are not like interferometers can easily make on a silicon and integrate the concept. And that's a very long delay. Why? You can make an upwards and or sometimes it also it's a good also. Fiber optic relay lines also are used now in our it's not correlation in all. That's all. I think we can go to the last one. So there are from different papers have shown the last 20 years, a lot of developments are there beyond talking to people. Keep many people out there at first. However, people colleagues. Now we have already finished one learning. I'll show you one example of what we did. I just will spend $1 million. So this one I use 0 1 mode or 1 6 state, E1 for different chemical state. There are a lot of interesting differences you find. For example, the mode field patterns are different. Their information constants are different. And if you look at the quantum eigenvalue problem, fascinating, very interesting problem. And it's not 50-50 problem like what in the beginning is a PDF is some distribution and so on. For interesting subject. As a specific example, the middle one what you see is a Y branch. Traditionally, if you have optical power, it can divide into two. First port half power is controlled half the power. Whereas if you use it as a for copper qubits, then you can observe that if you unit qubit states and also the upper wavelength, you can observe that 0 plus 1 is down. So it's acting inherently as a harmonic gate. So such operations you can use. For example, you take a ring resonator double bus and then two input ports and two output ports, you can achieve many, many functions. A lot of logic operations can be done. I think in the near future, when people get onto quantum logic gates, they will use ring resonators with different input output combinations. It's a look at the wind actually. The technology I'm not showing you, but we use what is called photonic band gap switches to build the actual circuits like this fiber mesh. So we can make regulators. You can make gradients, problem gradients, this photonic band gap. There you can provide a very I think that's all I want to say. One of our students has worked on evaluating deviation for protocol using this course. We go. Include some more tasks. Yeah, then along the other faculty, we are trying to generate single photon sources, correlated photon sources, etc. using this integrated file. So that's another form of students. Of course, not all of them because and show you that already the controllers. So one of our students was one of the earliest student worked on algorithms using photonic circuits, quantum algorithms to translate into photonics. So I have worked on random number generation and device independent protocols. Uh, yeah. So Bhavani has combined some interesting thought. Of course, right? Already more than 5 years. He has done on combining machine learning. Not exactly machine learning, some traditional algorithms like CNN, how they can be implemented using now. It's both classical way as well as that's all. Thank you very much for listening. We can have some discussion. Of course, I know that I have very, very cursory overview and deliberately avoided mathematics. I hope we'll have more detailed discussions during this soon because 8 days is quite a long time to learn fully. And I hope many of you will know that there are a lot of good books in this. And if possible, in the near future, you may have to introduce quantum information technology or quantum computing in your curriculums. These are all close by. But next 10 years, as you know, is the VLSI era. And then all these machine learning, etc., translated mainly towards VLSI. And into the future, after 10 years, it will be quantum and but we should get ready now. We cannot suddenly jump into that. It's not like IT revolution. In the IT days, in the beginning days of IT, people were simply given training in some software tools and then they can do all the IT jobs easily. It's not like that in one. First of all, the basic understanding of the quantum phenomena itself is very odd for electrical engineers. So this is the what critical is. I suppose there may be some discussion electric independently on how we should handle because see this is an ability based work mainly towards faculty members. So we should debate how this technology will shape into the near future. Okay, thank you.
Questions from the participant side, students?
Yes.
Electrons are replaced by right.
Hmm. Yeah, actually, right now, if you see quantum technology, there is atomic states. You have color signals in some solids with what different states. That's one of the properties. It can happen at room temperature also. Other one is NMR. And then what you see the big machines, the picture of IBM and all those are all atomic systems, large cooling and all those needed. For 16 cubic system as well, they will show grow. So that is the effect. And recently the pictures must have seen on the chip. On the chip, most likely they will use electron phenomena inside the chip. In the sequence of gate, they are crossing gate junctions. That part phenomena. You can use them to replicate. It's not only listening, the functions, quantum functions are possible. Yes. Mhm. What truth table? Is it a good table? Truth table is what logic is. See, suppose I is science of qubits. Bob has to say see, ideally, what the question of starting is they have only one basis. Horizontal vector college work. And then send horizontal. Yes. That is simplest chain over thing. But why we need the protocol and some we want to introduce the security aspects. So you see, they are doing randomly, let us say the point of sight. In between some we interpret whoever, even the receiver, is not sure about the outcome. Whether the outputs using specific basis. But in the scenario setting, how can Bob receive? This is that is the question. Then the behavior protocol came out saying that Bob also used a random basis and randomly select. Then the lookup table was. The lookup table will contain only the correct case that will be discovered. We have to all the entries to show that 50% of wrong. If you work out 50% wrong. And I said, if there's E in between, at least that Bob will check and in the same table, they will see only 23% entries matching. And they cannot match it with all the other reports. That's what it is all said. The only one this is one to one. There's no complex statements. But if someone taps into it, it will get it. QKD is they even take your proprietary. Yes. But otherwise, no. No. What is the say? See, suppose they say we are using the video. First, they should establish a picture with whatever second. And then keep on sending qubits using randomly these two places. And then one saying this is one, this is zero, etc. You can change a lot of things there. For example, 25% of the time I will use the first basis, 75% second basis. Bob also can say I will use only 50% first basis, 40% second basis. Then you can calculate accordingly. In that case, not simply entry table, you have to calculate the average probability of a single entry. Once again, please. I want to that to be safe. To be fair. Because there's some things that they have system. Is there any possible to person? Oh, yes, I got your point. So, what is that we are not introducing. We didn't say that they are changing. When we are showing that we are speaking many well, if you want to introduce ecoherence, or if something is changing, that's a different problem. You can devise some protocol. There are protocols now which will ensure so ecoherence. Say it is 90%. Uh, so much because so much. How do you handle? And or yes. And I need to decide. Yeah, already there are things you have worked out. And there's also the subject, popular subject of quantum error correction. Like in the classical, you can explain the extra ways. Then how the things, whatever, lot of things can be done. That's one of the first idea. But relatively, they're low cost. Cost low cost. The cost of our cell phones and laptops is all mainly because of the manufacturers. They're trying to push up. The cell phone should not cost $50,000, something like this. If could real estate developed in India, they can be less than 10, whatever. See, the phones will be half soon. So that's a different problem. The technology we don't have. See, if you want to set up a quantum lab in the college, it's very hard. You cannot easily generate a single photon sources and all this. In IST also, even when I'm doing there 400 crores, they are not expecting quantum like that. It's a big building up. 6 floor of that is not for quantum. But you see only high speed servers are a lot of furniture, almost empty. You can just come and see. They are getting ready. Every day they are debating what am I use. It's a problem. For this for this. Because see, I think the first level of development will take place at once on semiconductor devices. We'll find some corner where student states and CPUs with some electronic states. On semiconductor state, not only the masters. Like you have balance and etc. You define some of the energy levels. 2% in the states. And then the management by changing gateway or you can use so you can say this to its state levels or some combination. So electronic techniques is really very beneficial. Yeah, you are going to current case, lot of because there are so much conversion goes. We are going to basic things like standing, we are going to alter limits, or light knowledge, all the way. Very question along go lot of physics will be involved. That's an important problem if you want to impress upon your colleagues or students to study this subject. Superficial knowledge of the world. See, there's a QSC is there. We free there. So all these logic systems, quantum systems can be simulated without too much understanding about the physics. This no every develop like very engineering displays, people are spending 2000. See right now because see also they will be able to solve coding and all the things. But when you go to basics, they cannot. They so what is the problem? They will not be able to invent something new. That's what is needed. We should not be afraid of linear algebra is random process and linear algebra needed. So what are the benefits of linear communication? Basically, what Kika is one of the most popular ones. I think the DRDO labs also has built a Kika link. Yes, sir. I mean, it's there the next school. I know about the project was called in Hyderabad. There were all these private one of the meetings. They were buying all these resources. It is related. There's I understand the Hyderabad clinic from part of it. So they have also announced. I think it's already correct. But most of the news I found to go deeper is not really similar. See, for example, that Chinese experiment is well known. They have demonstrated 1,200 kilometers. One of our students was there in their lab, like girl from MIT University. She joined as postdoc. The Chinese was, I don't remember the name, Jimping Khan, right? The lab she has joined. And when she came here, we asked her about that to date. So she was able to tell everything. But how do we embed these cubic states into that so many kilowatt of optical power is transmitted that they don't disclose. So we have to understand this. So a lot of interesting things are there. We should know little bit, not really, not understand everything. I think. For a lot of interest is there. For those who are interested, please join IEEE Economic Society. There is a journal called IEEE Journal of Formula Price. So that over the last now it is 60 years of IEEE Economic Society. So a lot of developments have taken place and a lot of papers coming up. There are a lot of important papers. IEEE Economic Society itself is very lot of quantum stuff is going on. Not only quantum, other optical communication, all those things are there. And in your colleges, you want to start photonics subjects, please let me know. We have an active photonics society, language. And I suppose this college also would like to start a photonics society chapter. Are there any students of your college here? I know you have a student bench, I know all your other society chapters also like Comstock and all. I think that's why we think if you want to do fun. So I hope one of you, everyone's had request to take initiative in form of startups. Will help. The programs are developed quite dynamic. There are many programs, like student internship program is there. The last 4 years they have been doing. Then they are also looking at for members are small members. They also have a collaborative program. We had some collaboration with Asia some time ago. Russia is a very good someone an opportunity to go to the Russian quantum center. Very very all optical experiment. Of course, all they have a big gymkhana like area with all the optical experiments, optical cables, so many optical cables. Thank you.
You very much, sir, for the insightful talk on quantum information technology. Uh, We gained tremendous information on the basics of quantum theory, quantum internet, quantum satellites, and photonics, etc. And we are happy that you also shared some of the work that has been done by you and your team, and we are grateful to that. And we thank you for accepting our invitation and being part of this event. And I would like to request you can answer. Since the Yusuf sir has come to kindly join and please present the token of appreciation to the children. Sir, request all the participants to kindly join on stage to the photo. All the participants join by phone. That's it. Good afternoon, everyone, and welcome back to the second session of the FTP on emerging trends in quantum computing and AI for academia and research. We have with us Mr. J. Kanindra Babu, speaker for the second session, who will be talking on beyond binary, the quantum paradigm shift. He is currently working in Zen Shastra as an ML engineer. He has done quantum computing course at Los Angeles for 2 semesters, internship at Raman Research Institute, and ISRO on quantum computing. He has given many seminars on quantum computing at different universities such as DSE, Global Academy, HJBIT, Jain University at Davangere, and so on. I request Dr. Meherna to kindly welcome Mr. J. Kanand Babu. Thank you, ma'am. Welcome, sir. And over to you. Yeah.
The presentation is good. Presentation is very good, but for the speaker, the
Very good afternoon, one of our present here. Myself, Panika. No, that's it. It's really, really exciting to be here at Diamond Sagar to my hometown because this opportunity is one of the most incredible things I've never experienced before. I've given a couple of seminars everywhere outside, but this is something really different from me. So thank you so much for joining today, and let's get started. Well, I request everyone, it's a very warm welcome to the quantum world, right? So we'll see what exactly is quantum computing and how it is really different from the things which we see, right? The supercomputers and everything. Pretty much everyone knows about everything, right? Like ChatGPT, DeepSeek, Grok, AI, Grok 3 AI. There are some AI world war happening across every country, And quantum is something where, okay, don't worry, I'll be there. I'll be helping, not for the war. I'll be helping to manage everything. It's something incredible. Check this out. So, yeah, just the next one. No, not that. It's I always like Albert Einstein because he is the one for my inspiration towards quantum world. Because see, I started learning about quantum mechanics and the relativity, everything right from class nine. Because I was so curious to know what exactly the quantum world is. Because we studied for classical physics. What about the quantum stuff? There are a hell lot of things. There are so many things, so many theories, so many string theory, everything. There are so many things. I'm very much curious to know. So I always insist my audience, if you have any questions, feel free to ask all the questions. I'm happy to answer. Okay, excellent. Well, today we'll see about what exactly the quantum mechanics is all about, quantum computing, and why we need these quantum computers and where are we using these quantum stuff and why quantum computing is so faster. We have supercomputers. Why don't we use them? Why quantum? That's one of the greatest questions, right? So we need to know why it is faster. And we also have how these quantum computers work. One of the most important questions because knowing what is quantum, that's fine, but we should also know how it is actually working so that we can use in any other applications, let's say R1 applications. And next, we'll see the qubit game, something quite interesting, that was launched by Google. And I'm happy to announce that Google started their own, quantum stuff like so many years back. And recently, they have announced, not recently exactly, they have announced Willow, the quantum chip. I think pretty sure you are aware of it, right? One of the game changing guys. Really, I must appreciate that. Because quantum chip is something, it's just a part of quantum processes. It's not exactly representing a process, an entire process. It's a part, it's just a minor thing, right? And there was one question from NVIDIA. Well, I was taking, I was attending an interview there. They asked one question. How will you represent eight, you know, eight in bits? 8 in bits. How will you represent it? It's just 100, right? How do you represent 6? 101. 101. Okay, how about this is just binary, right? We use 0 and 1, that's it. How about I use 3? 0, 1, and there's one more part 2. Something incredible, right? Something crazy, seriously. That is something not 2 0. Here we use 2 bits, right? So we keep it as 2 power 0, 2 power 1, and 2 power 2, and so on, right? But representing 6 is pretty difficult in terms of like 2 qubits. Maybe yes, but when we come across the time and space complexity, it's really tough. So we switch to 3 bits, which is 0, 1, and 2 actually. So at the time it will be 3 power 0, 3 power 1, 3 power 2, and so on. So it will be 2 and 0. 0 for 1, 3 power 0, and 3 power 1 is 2, because 3 plus 3, 6. Make sense? Yeah. So this was the tricky question that they asked. I kind of answered because I knew this about qubits. Qubits we usually know that, right? Quantum bits. We generally say. In short, we say qubits, right? There's also called as qubits, which takes 3 things at a time, right? We can see across the balls. Quantum mechanics. I don't think so. I need to really say that yes, this thing takes 3. Hello. Quantum mechanics is something where we deal with the more of smaller molecules. We study more of atomic properties. Especially we deal with a lot of electrons because that's one of the major things which we see what exactly is happening on, right? Because see, electrons are something which shows their properties in more incredible way. Let's say your minus 1 plus 1, the spin, right? That defines everything. I've studied in nanoscience. nanophysics, right? Even there also we come across with a lot of stuff, like a lot of revolutions, microscopes and everything. That all depends on the electron spin. Even with quantum stuff, even in the quantum computers, we come across with this. It's just a play of qubits. It's just a play of electrons, photons, and everything. Next, what is quantum computing? Let's break down the words. Quantum and computing. Quantum, yeah, is something where we fundamentally study about quantum, the smaller chunks like atomic structures and everything. Computing is something where we have computational power, right? We deal with a lot of logic gates and everything, circuits, where we build all these we can approach it. Okay? So quantum computing is something. See, if I have quantum mechanics, then this goes to quantum computing. I'm very much inspired by you, so I'm going to use in my computation power. Very simple. But any questions so far? No? Okay. Quantum computing is something like that. I am inspired by you, and I'm going to take your few properties and I'm going to use it in order to speed my process, in order to speed my time complexities, space, reducing all of the space complexities and everything. Especially when we deal with RAG applications, retrieval augmented generations, right? So many of the companies, top like Microsoft companies, Microsoft, Google, Amazon, Facebook, all these companies, okay, they deal with the graph RAG models, the graphical representation of RAG model. Why? Because we have so many LLMs, right? We don't trust LLMs at all because some or other way it can leak out the information, right? So we don't trust the LLM. So individual companies build their own models itself. Let's say OpenAI, ChatGPTs and everything. And one more, ByteDance, DeepSeek. ByteDance is something where you see TikTok, right? That was constructed by ByteDance. And that's the applications, right? And even Google, Gemini, all these people, they don't really trust on not their models, but different models because somehow or other way, it can leak out the information. So when we come across with a lot of RAG models and everything, because we need a proper, precise answer. I can't put all my company's data into model because that's going to be a breach. That's a data breach. That shouldn't happen. That's a huge loss to the company, right? There are costs happening here. Like so much of data is being, invaded. In order to verify, see, we have storage. See, one thing is we can't ship the data. We can actually ship the models, right, from one place to another place. That is less expensive. Shipping data from one place to another place. Because shipping data is like huge. It's like very much expensive, right? So at the time, we have to reduce space. Quantum is there. Quantum will say, don't worry, I'm there. I'm going to reduce all your problems. I'm going to sort out all the problems. Don't worry. I'm there, right? That's what the quantum saying. Next one. Okay, we'll understand more of the concepts. When I was doing an intern at University of Cambridge with one of my friend, Jung, his name is Jung. He's from Korea, South Korea. Me and like we both were writing a paper on quantum communication systems. It's quite, confidential. Dr. Connie, she's from coding school itself, and she is helping us to write a paper on that. And one of his friend, she has a YouTube channel, and a couple of things that he shared with me as well. Okay, the first thing is it's a quite task for everyone here. The first thing is understand the given map here. There's a map with a lot of things in the map itself, right? The blue thing appears to be as ocean, and there are some trees, rocks, and everything, right? So don't worry, I'll give you some tools to explore that. So these are the tools that I'm going to give you to explore the previous one, right? Yeah. The tools are no computers. We are no computers, right? And horses are considered to be early computers. And let's say your cars appears to be a modern computer. Let's say your supercomputers or something like that. Like even your laptops as well, right? Okay, I'm going to pick this guy. I'm going to take no computers and let's explore the map. See, as we can see, there's some, some people exploring the map. Even it's very simple example. What is 12 into 12? 12 times 12. 144. What is 144 times, let's say, 2? 288, right? It's a very simple basic mathematics which human can actually do it. What if I say 144 times 144 times 144? It's typically huge. I mean, I can't say that because I'm not a human calculator, but it's not really important, right? Because that calculation, what we used to do, we pick up our calculator and we solve it, right? With the help of calculators. That's human limitation, right? There are some exceptional, I'm not talking about that, but for normal common people, that's a limitation for human, right? Even in this case, even for early computers, there are some limitations, right? Then we come across with modern computers. See, there are some limitations where human doesn't know what exactly is happening out that side. They doesn't know. There might be a threat. There might be some, animals or something where it can chase down him. There are so many things, right? We don't know what exactly it is. If there is an animal threat, he needs to come back faster and faster. He can't do that because it's out of his limitation, right? And then we have HOTS, which is early computers. Early computers have changed the path itself. See, we have new routes, new pathway to discover new things in this entire math structure, right? There's so many new things, right? Hasn't go. Let's say there was one person, he's a chief manager at Infosys. He mentioned that. Sure, if there are so many computers coming up, is there any threat to our job? He says only one thing. Even though the technology is growing, there is no way that humans' jobs are at loss. Of course, not in all. And even it's the same case, even AI comes into picture, even quantum systems comes into picture, there is no threat to the human job. The jobs will be there and jobs will be increased. See, now you can see, right? Computers are there. There's no loss of jobs to the humans, right? There are more of rapid jobs, right? It's the same case again. As the technology grows, once again, can you come back or something? Yeah, cool. As technology grows and grows, we discover new patterns. We discover new stuff, new things in this math structure, right? And also, yeah, we see whatever we do, whatever the technology comes, whatever the DeepSeek, everything comes to the picture, we have some limitations. Even DeepSeek has some limitations. Server backup, one of the best example, because I personally was using DeepSeek more and more, and then I've seen there is a huge drawbacks. Server backup, server problem, and API integration problem. There were so many problems at DeepSeek. Since the DeepSeek performance is so beautiful and so nice, but still there are some drawbacks. Right? It runs with RL, which is the reinforcement learning with human feedback. Right? It's the same case. Even the technology grows, some limitations are there which we can't discover. Something like this. Area unavailable, which is undiscovered, right? And then we come across with modern computers. See how was before and how it is. Entire math structure has changed. A lot of buildings, a lot of innovations, the roads, everything has changed, right? Now tell me something. How are quantum computers? Is it a supercar? Is anyone here to guess? Because I want the session to be interactive, not the thing which goes one way. Any guesses? The question here is quantum computer a supercomputer, supercar? Helicopter rocket. Okay. It's something I'm expecting more. Transformers? No, no. Any guesses? Any guesses? It is a boat. We forgot about ocean, right? At the starting we had and also we had ocean, right? We forgot about that, right? Now this is a boat. Let me tell you the next example. As you can see here, the supercomputers, especially the supercomputers, can explore only this structure, only with this respective map. That's it. It cannot explore the undiscovered parts. It can go. I'm not sure I'll be available at that time because I might be dead. Because it takes billions of years to discover that. To discover undiscovered, right? It should be discovered until before I die, isn't it? Before I die, it should be discovered so that I can get to know, okay, this is something like this, something like this. So I can just work on it and then I can give some contributions on this and put it on the world, right? So people can use it as a great things, right? Great things can build from that. The partner will help you to explore these maps, these undiscovered areas. But that's really clear. Got it? Any questions so far? Okay, just one question for everyone. What ocean is all about? What does it indicate? Okay, we see the math structure. The math structure is nothing but our problems, right? On top of that, our problems, we build a lot of technologies. Let's say car, human, horse, car, modern car, and then we come across, we change the math structure because that's what we build solutions on top of the problems, right? To omit the problems, right? And now, what quantum computer, which is a boat, it is traveling to undiscovered patterns. Fine, cool, super cool, yeah. What about this ocean indicates? Sorry. Yes, somewhat acceptable. Where it is acting, obstacles. Okay. Any other guesses? Sorry? Data. Data, yeah, maybe. Problem solving skills. Mm-hmm. There's one super word. We are just, it's like AI, ML, DL, GenAI. GenAI is a subset of all of these things, right? Subset of DL, subset of ML, subset of AI. We are just referring all these things. All we are referring GenAI, DL, ML. We are not saying what is AI. No, I am that word. Have you heard of complexity classes? We have P type, NP problem, NP hardness. That comes into picture. There's no, that's multi-billion dollar question. P equals NP. Is that plausible? Of course, it's not plausible. Not even with quantum, I guess. I'm not sure. Maybe it can use some wonders because I'm not sure. And this motion indicates that patterns. We have one class, let's say P, and we have NP, right? And things which we see between P and NP, right? The gaps, that is motion. That is motion. NP problems and NP hardness, let's say, how many of you guys have played Candy Crush Saga? Candy Crush. Cool. Oh my god, nice. Candy Crush is something comes under your NP hardness problem. That's an NP hardness problem. Right? And this is something like that. Ocean indicates the collection of all the problems which are considered to be P and NP as well. And we are just moving across that to see what exactly is like. See, we are just thinking in two-dimensional cases. We need to even think and perform ourselves to third dimensional as well. Because third dimensional is something where you see the things in a different way, in a most incredible way where we can't even imagine, right? And that's the most important point to make in this idea, right? Discover things. One thing is simulation nature. Stimulating thing. What does that mean actually? Because I can't build my super quantum computers right in my home because I don't know. I need to sell my properties and everything because it's very expensive. Because only top MNCs are having this quantum stuff. Like let's say Google, IBM. IBM is one of the best. Not even Google usually. These companies, or even Amazon, Microsoft, all these companies hold this quantum systems. They really build quantum systems. I had MIT tour as well. While I was going with the course at Los Angeles, I had a tour with MIT quantum lab. There they build like really good quantum stuff. That's very incredible. That's very interesting as well, right? And simulating nature, where we see where we get the quantum stuff, where we get quantum stuff into our plans. Right? We are just simulating it. We're not really building it. We are just taking some sort of insights, some sort of things, putting in our system and working on it. That's the best thing. right? That's the best thing to explore more of quantum stuff, right? That's the most incredible thing. And there's one more good news. Sorry, it's not a really good news, I think. But in the quantum world, of course, that's a really great news. This quantum, there are some algorithms called Shor. One of the greatest, algorithm, Shor algorithm. The Shor algorithm is something, it has broken RSA algorithm. RSA, people who are service related, maybe everyone might know about RSA, right? A bank accounts, everything is being secured. Now there's a huge threat once if this comes into picture, right? Because this has broken RSA. That's a huge breakthrough across the world. Across the world, seriously. That's a huge new discovery things. And one thing is encryption. One of the most important things, encryption. Because whatever we do, it should be very secure enough. Even if I build my, let's say, even if I build my applications to Morgan Stanley, Bank of America, all these top tech people, I need to make sure that these applications, whatever I build, should be safe enough, should be safe from all cyber attacks, right? Encryption in quantum, we say it is called as quantum key distribution. Okay. A quantum key distribution is something where we see the things, where we keep all the data very secure. Even suppose, for example, I am sending hi to him, right? In normal classical system, if I, let's say, those two people, they're just chatting mutually, okay? Now, if I interrupt and see the messages, even they won't know that, okay, some third person has been entering into our conversation and just checking out all the messages. They won't know that, I'm pretty sure, in classical. Whereas in quantum, it's not something like that. I'll tell you why it is. There are a couple of slides. And one more important thing. What is ocean? Complexities, right? We have seen in two dimensions, right? Even inside the ocean, there are so many mysterious things happening. Even in the inside ocean, we have a couple of layers of simulation, encryption, so and so, so and so, so and so. There are so many things. See, that's what I told you. Seeing in two dimensional doesn't matter whatever it is, it's gonna be simple and easy. But I don't like simple and easy. I need challenging things because that's where we learn many things, right? Third dimensional is something where brain rotates everything. Third dimension is such a super thing where you can visualize everything, imagine a few things. Imagination is powerful than the knowledge, said by Albert Einstein, right? Right? A very wise man. So even see, that's why in third dimension, we have to check it out. What exactly happens, not only in this way, even at the downstage as well. Right? Yeah, that's what I meant. Not only this, not only in two dimensional, just traveling across all the areas, it's even inside the ocean. We need to know what exactly it is, right? Yeah, this is something interesting, I would say. As I mentioned, modern computers are something like PC laptops and everything, right? And then we come across with supercomputers to handle a lot of complex data, right? Especially the researchers and top tech companies people, they especially in R&Ds, they use supercomputers, right? Even I've seen in IISc as well. Like a lot of supercomputers happening and a lot of research is happening out there, but huge complex data. If I see that, I'll be traumatized because I can't handle that data, right? So when see, I've seen you've seen quantum as a growth, right? When the technology grows up with let's say over 10 years or 15 years, now the growth continues there for sure. That's the thing, and that is the only way which we can discover inside the ocean. I mean, depth. We can see what's the depth of the ocean, right? How see universe is of course mysterious, and even the ocean thing is also mysterious. Even if we go deeper and deeper, deeper and deeper, deeper and deeper, still it's absolutely mysterious because everything we are in the middle. We are absolutely in the middle, top, bottom, and inside we have quantum aspect, something like that. Visualize the things, imagine the things. Very incredible, incredible. Okay, one of the good questions: why do we need quantum computers? Why? Why do we need quantum computers? Because there are a lot of research applications, so much of data, so much of complex data that we need to handle, right? There's huge data which we can't even imagine. So handling the data is very simple, right? When we go with super. But sometimes I told you, even the technology goes up, there are a lot of limitations happening with that technology as well. Even supercomputers have limitations. That's example. Will the quantum chip announced by Google, right? Over a decade they were working on chip, and finally it's out, right? Supercomputer, there is one problem. Okay, there's one problem called random sampling circuit. Okay, this is a benchmark, right? This is a big problem. And this problem can be solved by supercomputers and quantum chip as well, right? Supercomputer took 17 years, 10 septillion years to solve this problem. Septillion, how much? 10 power? 10 septillion. 10 power 26. 10 power 26 years. I can't even imagine. It's way more than the age of universe, I would say. Right? It's way incredible. And supercomputer takes that much of time to solve a problem. No use. Because we need faster results, right? And just below just below, just a quantum chip, not a processor. A quantum chip took how much time? Can anyone guess? It was in the record. It wasn't out of the record. It was in the record. How much? How much time? It's 300 seconds. It's 5 minutes. Such an incredible thing. Crazy innovation, right? Such a huge thing can be solved in 5 minutes. Wow. Impressed. I love that. Really? Isn't it, right? Such an incredible thing. How it is happening. How it is even happening is because there are so many things happening out there, right? We have to know each and everything. Now, how supercomputers are something like this? We see electrons, right? We interact with electron. We never seen electron, but we interact. We feel electron is there, right? Isn't it? We feel electron is there. Now, let's say, imagine. I want everyone to imagine. Imagine there is an atom. Okay, there's an atom. Think that that's the ecosphere or ecospace or something like that. Okay. So these electrons, which is there in the atom, let's say that has a data. Think that has a data. Now, an atom, this is electron, right? This one is electron. It's somewhere here, right? Cool. There's one guy. Okay, let's say my simulation is here. Okay, my simulation is here. Now, nice. I'm producing heat to this fellow. What happens to electron? Starts vibrating, yes. After that, if I put more heat, get excited. Exactly. And next, let's say, Tata, bye. There's so much of heat, I can't handle it. See, good night. It leaves the ecospace. It leaves the atom, right? Now that's the most important thing. It can hold the atom, it can hold the electron in the atom when it is cool, when it is more cooler and cooler, right? So when we can't have quantum systems in our brain because it needs minus 126 degrees Celsius. It's in the record again, and that's almost equal to space temperature, right? It's almost equal to space temperature, where you see across maybe Mars, somewhere around Mars or something. At the time, in nearby Mars or something, it records minus 126 degrees Celsius. It's absolutely brutal because we can't handle that, right? We can't handle around minus 10 degrees or something, right? Typically, right? Even I can't handle it. I can't handle 0 degrees though. That's different case. So that's the point. We can't establish our quantum systems. Now that's the most beautiful thing. If I want to handle data, if I want to handle electron, I need to be more cooler and cooler. If I'm hot, if I'm heated up, I'm cold because that's it. I'm hot. I'm going to lose data. I'm going to lose electron. And some other electron who is way cooler, let's say some other atom is way cooler, going to grab that electron. Simple. Going to grab that electron. Very simple. Because I can handle the data. That's what we say. Once the data is created, it cannot be destroyed. Whose principle was this? It was from, I studied it first period. Whose principle is it? Uh, the thing is, once atom is created, it cannot be destroyed. I meant once the data is created, energy, yes, it will follow. That, yeah. Even further experiments, couple of experiments has mentioned. He mentioned it as well. So we are taking few insights from quantum mechanics itself. We are not getting anything. We are just taking few insights. That's typical, a normal theoretical part as well. Because where our quantum computers are used, it is used in everywhere, guys. It's used in ML, it's used in DL, it's used in weather forecast studies. It also uses in supply chain optimization. How Swiggy can deliver a super good products to our home. It's all because of supply chain optimizations, right? And there are financial model modeling and optimizations. Yeah, one important thing that I want to share because in Zen software, where I'm working with the client, Morgan Stanley, we provide, I'm building an agentic AI system for them. Okay. Couple of things. There are so many financial records, right? We need to build a system so that people who want to revise the financial records should be very easy on them. They have so many records. Let's say they have some thousand records. I can't open each and every record and check what exactly it is, right? I need to make it more optimistic, right? That was one of my projects that I'm working with Morgan Stanley. So it's again, financial optimization again, financial reports optimization, where it can optimize each and everything. And again, one more important thing, security concerns. And I need to make sure that everything should be very secure, right? I can't just expose companies' data to public. That's a huge, big loss to the company, right? We need to make sure things, whatever we will, even in our daily life, even our projects, whatever we do, make sure keep them secure. Make sure use some differential privacy methods, something like that, to make it more secure, safe, and prevent from unauthorized sources. Right? That's the most important thing we can. There's a quick IBM video, the quantum technology. So I would request you to please check out. Yeah.
IBM has unveiled the most powerful quantum processor in the world, the Osprey, which boasts a massive 433 quantum bits. The new chip headlines a raft of advances in quantum computers that the company has announced as it prepares for a massive leap next year. While they've served us well for decades, traditional computers are increasingly paling in comparison to those young upstarts, quantum computers, where the former stores and processes data in binary bits as zeros and ones, the latter uses qubits that can be 0, 1, or both at the same time. This exponentially raises the processing power for each added qubit, allowing them to potentially perform calculations that are impossible for conventional computers. With the power of 433 qubits, IBM's Osprey is the most advanced quantum processor in the world by a large margin. It packs twice as many qubits as the previous record holder, Xanadu's Borealis, which was tested with 216 qubits, and over 3 times more than IBM's own Eagle, announced last year, which packed 127 qubits. The Osprey has a similar architecture to its forebear, being comprised of a single layer of qubits atop several layers of control wiring, which helps cram more qubits in while reducing their error rate. An integrated filtering system has now been added,
which helps reduce noise and improve stability of the device. IBM says this machine's number crunching capabilities far surpass any traditional computer, claiming that to represent a state on the Osprey processor, a regular computer would need more bits than there are atoms in the known universe. IBM also announced some other tweaks to its quantum systems. On the software side, error correction has been improved and users have been given the ability to more easily choose between increased speed or precision. The overall control system hardware has been upgraded to control 400 qubits per rack at a lower price than previous versions. As impressive as this year's updates are, IBM is looking to next year as the real turning point. The company's roadmap says that next year's quantum processor, the Condor, will boast a stunning 1,121 qubits. Also on the cards is a modular processor called the Heron, which stack multiple 133 qubit units together to make more powerful quantum processors. And finally, the IBM Quantum System 2 will be released towards the end of 2023. This modular system will form the framework of the company's quantum supercomputers, housing multiple processors with communication links between them. These are all stepping stones on the path towards IBM's plans of building a quantum system with over 4,000 qubits by 2025.
One of the most important things that I need to mention, quantum error correction. Even while a lot of experiments on Willow, it's something like there are certain qubits, let's say 50 qubits, okay, there are certain 50 qubits. If it crosses more than that, the system doesn't act as a quantum, it acts as a classical. What's the point? There's no point if it acts as a classical stuff, right? If it is below, then there are some overfitting and overwhelming problems. So one important thing is quantum error correction. Even though if I increase qubits, it shouldn't act as a classical system. It should act as a quantum system itself. For that, a lot of algorithms comes into picture. Quantum error correction algorithm that I mentioned while once we launched the qubit game. Right? Thank you, Arvind, for this video. Yes. Now, why supercomputers are fast? I want one volunteer to be on the stage. Anyone? One volunteer? Okay. Right. Okay. Now he is, let's say he is qubit. Okay? A qubit. Qubit, okay, this is a fundamental unit which we use in quantum systems. Like how we use bits, right? Qubit is something like that. Quick. Your observation is towards that wall. There's a brick, right? Your observation is there. You shouldn't turn around. Focus direction. Okay? Good. Now, can you set some waving a hand or something? How about here? Seriously? Okay. Thank you, man. Thank you so much. Just a quick demo, anyways. What happened? What just happened? He was here. His complete focus was on there, and still he can sense. Even I'm waving my hand. Even I perform my actions. Still he can sense that. How is that even possible? How? Now that's the definition for superposition. Superposition. Exactly, right? That's one quantum property which was used in quantum mechanics. Superposition. Two things at a time. If I toss a coin, the end result will be either heads or tails. That's 0.5%. I mean 0.5, right? It's a 50%. 50% chances of getting either heads or tails. The quantum says I can get both the stuff. Incredible. What? Crazy. What? I should, even if I toss, toss a coin, you write in the India versus Pakistan, it should say, you both play both. How is that even possible? It's crazy, right? The quantum says that. Now, what's the major motto here? It can reduce everything. It can store much data. Now, tell me something. Is number one, like the real one, is an infinity number or just a constant? It's a prime number. Okay. What's that number? Is it constant or it's 10 to 1? Like how we say limits x tends to infinity, right? Is it 1 tending to 1 or just a constant 1? Constant 1? Okay. Okay. Now, what represented in terms of infinite series? It's a geometric progression, right? Half plus so and so, so and so. Half plus 1/4 plus so and so, so and so, so and so. Right? That's an infinite series which tends to 1. Right? Now, my question here is in between 0 and 1, how many values are there? Infinite values, which means which means I means the quantum. Okay. Now I means I can store so much of data between 0 and 1. I can represent data in between 0 and 1. How about that? Not exactly 0 and I represent both at a time, which means it's talking about intermediate. It's talking about between 0 and 1. That's the incredible thing. But that's what it makes the quantum system move faster to explore everything, to represent the data and explore many things like visualization or analysis, everything, right? It can make faster and faster. And that's the motto behind it, right? How do quantum computers work? Okay. Quick thing. 2 into 6,
Right.
12 into 11. Okay. 132 into 2, 264. Right? Okay. 264 into 275. Stop. Isn't it? Okay. How about I change like this? What are, just name one factors. Okay. What are factors of 12? 12, right? 4, 3, 2, 6, 6, 2, 1, 12, right? So now I give 15 digits where I don't want to mention that. I might give my phone number too. And then I'll ask, give me factors of that. Quick. 1 to 11, of course. Other than 1. It's one number. Okay, fine. Other than that, it's it might be possible, but you need some time, right? But if I say quick, and based on the last number, let's say it's a prime number. Let's say it's not a prime number, but it's a pretty huge big number. Let's say it's on 20 digits. Okay. It's in, yeah. It's a real number. What if it's not a prime number? Then it's tough to find other factors, right? Other than one and its number. It's really hard to find, right? Typically, even I need some time to find out. Now, sure algorithm is something you can find these factors along. Something in sure algorithm. You can check out. So, sure algorithm is something where it breaks down the complete number into two chunks and then it separates everything. And then it finds the real factors and gives you the end result. And the process behind all these things will be way faster. One more important thing. I'll explain Grover algorithm. It's also called as a Grover algorithm. Very simple. Simple. So, now he is a classical computer. Okay, he's a classical computer. And okay, that's it. Now he is towards my left, he is a classical computer. And towards my right side is a quantum computer. That's it. Okay? Now you're doing tasks for both of you. The task here is password detector. That's a simple task, isn't it? Right? You have four, let's say pin code. Let's say there are 4 digits that you need to enter. 4 digits you need to enter. Right? Okay. I'm the user. I'm going to enter 4 digits here and here. It should detect my right password. How many chances are there? 16? Too powerful. 16 possibilities, right? 16 possibilities. In that, 15 is, of course, it's incorrect. Isn't it? 4 boxes. Let's say only 0 and 1. I'm just reducing all the complexities in order to understand that. Let's say there are 4, okay, and 4 boxes. Each boxes are represented in 0 and 1. What are the couple of chances to bar 4, which is 16? In that 15 are incorrect and 1 is isn't it? Is a classical computer, I mentioned. What's the worst case? 15 times saying wrong, 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 wrong. First time, yes. This is your password. Finish. But the time taking here is, let's say, 2 seconds, something like that. Okay. Now let's switch to our quantum computer. It's quantum episode. Okay. How many chances are there to get like how many incorrects are there? Of course, it's 15, right? One is the one that's correct. Here in classical, how does it check? It checks first 0, 0, 0, 0, no, 0, 0, 0, 1, no, 0, 0, 1, 0, no, 0, 0, 1, 1. It checks every time. The worst case here is 15 are wrong and 1 is right. Let's say the password is 1010, somewhere around there, right? 15 wrongs and 1 right. Here it is not like that. Here, the qubits are represented so differently. It represents something like this 1, let's say 0, let's say this is 0, 0, 1, 0, 1, 0, all the 4 boxes. It's not like the golden ratio. It's not the golden ratio. It's like top of that. It's like right. That's how it is represented. By using Grover operator, we separate the right ones from the wrong ones. And the time taken here will be around 0.00002 seconds. 7 times or I've seen one research paper, it was announced that it is 50 times faster. 50 times faster. For it's not for smaller case, it's for bigger things, very much bigger. Let's say you have like 17 to 20 digits of password, then it's hard, right? At the time, it takes a lot of computation process. At the time, it helps a lot. But that's the fastness. Like that's the best example of Grover's operate how it works, and that's the beautiful thing about quantum stuff. Thank you, man. Thank you so much. Thank you. The next one. And one of the most important things, what superconductors? It's a pretty bad thing I feel to ask superconductors all these things to my physics teachers, right? What superconductors? Super, yeah, precise. And there's one MIT research where seen in 2022 or something. MIT research people said that superconductors can be used at room temperature. It should happen at somewhere around less temperature. Let's say somewhere around minus 120, 130 degrees Celsius, something like that. At that time, it should conduct electricity, right? So that stuff, like that, it can be used in room temperature as well. There are high chances that we might get our supercomputers to home, right? Typically, right? That's a chance. It may not be a proper thing. It might be a chance. That's it, right? Now, one of the most important things to be mentioned, there are a couple of key properties of quantum mechanics which is used in quantum computers. One thing is superposition. I hope you know about superposition, right? The demo which I've shown. And the next is entanglement. When I was doing a research at RRI, Raman Research Institute, and at ISRO, we were working on quantum communication systems with this entanglement, because quantum entanglement is something, it's a base, it's like a base or key property to understand how the qubits communicate to each other, right? That's the most important thing here to be noted. So that's one thing. Just explain it through the demo video itself, through the game itself. And there are other properties which is interference, which we deal, and then see the things, one more important thing. In ideal match, if I toss a coin, either a player should choose one. If he wins, either he need to choose batting or bowling, doesn't it? Right? The results here should be either heads or tails, right? Which means, understand, I'm tossing a coin, it goes up, which is it is rotating there, right? When I toss the coin, it goes up, it's still rotating, which means it's a superposition. There are a couple of chances that it might get to heads or tails. It's a superposition. When it comes down, we are defining, yes, it's heads, tails, something like that, isn't it? At that superposition, we need to break that. If you break it, then we'll get to know whether it's heads or tails. Without breaking it, it still remains in superposition itself. For that, we use a measurement, which means we are breaking it. That's the most important. Next slide. Okay, there's a quick, launch of game on Qubit game, which was constructed by Google to understand what quantum computing is all about. Okay, I'll be showing that. There's 3 minutes. I'll be showing it. Qubits, of course, I was telling you that it's a fundamental components that are used to store information and process the information, right? In quantum world. And the quantum information, how it is stored and how it is performed, everything is again in the game itself. And there are multiple qubits. It's not, we are not just dealing with one qubit, right? We are dealing with a lot of qubits. Let's say we are dealing with some 500 qubits or something like that. IBM said with the end of 2025, they'll be constructing more than 1,000 qubits, right? So it's something like that. We need to understand it's not with a small scale. We need to think with the real big scale, right? So it's something like that. Coming to qubits, of course, I shouldn't lose my electron, right? I need to cool down my system. I need to cool down my echo sphere, echo space, right? And we'll also see the representation of qubits as well. These are the 3 representations of qubit. The first one is cat notation. That's a pretty good thing that I've used. The cat the cat is alive, cat is dead, right? So the cat notation basically the top physicist people, like almost all physicist people use this for their research cases. When we deal with a lot of complications behind algorithms or something, at the time we use this one. And the second thing is we use block sphere. Block sphere is something where we understand what exactly behaves. In this block sphere, as you can see, the upper points at 0, the down points at exactly 1. It's like 0, 1. What if it's something like here? Is there 50% of chances getting 0 and 1? If it's here, it's the same thing. But there is a difference between the right and the left. At the right side, we see plus, it's a plus state, and left side, we see minus state. That's a high level things to be understood. And the third important thing is vector representation. It's 1 0. 1 0 indicates probability of 0 and probability of 1. 1 0 vector, which means it's a 0 state. If it is 0 1, it's 1 state. What if it's 1 and 1? Both states, which means it's a superposition. We need to break it. For further analysis, we need to make it. And that's the case here. And computer can understand only vector representation. It doesn't understand cat notation. It doesn't understand the block sphere. It doesn't really understand that. Block sphere is something where we want to get understood. Like we need to understand what exactly happens to visualize things, right? That's what we use. And here you see 1 by 1 to 1 by 2, right? In cat notation. It is also called alpha and beta. Alpha square plus beta square is always 1. Probability. The probability of a cat being alive, but the probability of a cat being dead, same time in the minutes is of 50%. The chance of being alive at 50, right? That's sort of the wave equation that I can say, right? I've learned in first time again. That's one of the best concepts I've never heard. Quite really interesting. Yes. Sorry. Yeah. That's the thing, yeah. It's again representation. See, that's why we are getting insights from quantum mechanics itself. Putting into compositions, right? Putting into compositions, right? Putting into computation power to explore what quantum can do. Power to explore what quantum can do. That's what we do it. That's it. That's what we do it. That's it. Next, we'll see that. Next, we'll see that. We'll see this thing as well. Next, we'll see this thing as well. Next, yeah. Yeah, can you just click on it? Can you just click on it? Click on right here. Yeah. Click on right here. Yeah. Yeah. Can you start the video? Yeah. Can you start the video? I'm a qubit. The fundamental part of quantum. I'm a qubit. The fundamental part of quantum computing. Thoughts. Now you see. Now you see. It's getting ready. It's getting ready to do a lot of computation power, right? So they feed a lot of computation power, right? So the heat is here. Once the heat passes through qubit, it loses the capability. Once the heat passes through qubit, it loses the capability storing data. It loses, of course, right? We need to save that. So can you click on that right now? Plus. Okay, wait. Now have been saved. Hang on, it's been saved. Pause. Yeah. So can you just block that right now? Okay. Yeah. Can you click on that? Just click on it. Just click on it. So it can store information. We can start storing information. So it can store information. We can start storing information. Else, if the heat passes through it, it loses information. But that's the most important thing here. And not only that, when you see there is a blue mark, right? Blue important thing here. And not only that, when you see there is a blue mark, right? Blue mark over left right side, right towards my right side. That's an encyclopedia. It's a quantum encyclopedia where you can study more on quantum stuff. Like quantum stuff is a technical word, I mean, right? I use more of quantum stuff. That sounds so nice to me, right? So this is one of the most important things because we kickstart our careers with quantum stuff. We need to understand this thing. We need to play this game. And there's a certificate for this as well, you know. This is the most important. It's like 3 qubits. Okay? 3 qubits, how many states? 3 qubits. Okay? 3 qubits, how many states? 8 states. Right? If we have 3 states, let's say qubits, right? 1 qubit, 2 states. 1 qubit, 3 states. So to represent 8 states, how many qubits we need? Just two. 3 part 2. Right? 3 states. 3 part 2. It's like 0, 1, and 2. Let's say 3 part 2, which is 9. Right? 9. And 2 part 3, 8. Instead of using 3 qubits, we can use only 2 qubits. It's a space complexity time based thing. So, well, definitely think over. And one professor from RI, Urvashi ma'am, she was my guide when I was doing an intern at there. Ma'am, she was working at, she is working with this experiment itself, and she's working with her colleagues at University of Cambridge. Madam used to mention that. So instead of using 3 qubits, we can use 2 qubits, which is very easy and faster in progress and so on. So at the time, it will take over in some case. But again, it's a theoretical based approach that we see. And practically, maybe a couple of years needed for research and stuff. Any other questions? Physics. Uh, this is like a high level thing. It's like, see, for every, there's one psychological thing, wherever we go, let's say if I go someplace, if I was sitting here, which means I'm leaving my prints. Even though if I'm not present, I'm leaving my prints there. So it's the same case. Even if I'm an atom, I'm losing electron. To get the electron, there will be some place. Okay, there will be some place with myself so that I can retrieve that. It's like I'm just throwing a pencil and I forgot to catch the pencil. Let's say you took that pencil. Now I'm gonna since that pencil is mine, isn't it? And you took that. And I can ask you back, right? I need this pencil because it's mine. So I'm gonna take that. Again, you might argue, hey, this is my pencil, I took this. You can say that, but still, I can take that pencil because that pencil belongs to me, right? It's the same case, okay? To be more, because we have so many protocols for that. Let's say BB94 protocols, B92 protocols. We have so many protocols, quantum protocols that will help you to retrieve data back. Secure transformation of the messages, anything will be within protocols. Because it should happen within the protocols itself, right? To establish the communication system in the channel. So that's the case. Any other questions? Is the speed of light? Speed of light, approximately, yeah. There was one argument at quantum entanglement. This is like in the community itself. People say, for example, quantum entanglement is nothing but, let's say, I'm a qubit and he is also qubit. Okay. If I remove my jacket, what changes happen to me, it's of course going to reflect on him. Doesn't matter how far, matter if I am at end of the world and he is at some other end of the world. It doesn't matter. Still, what changes happens to me, it also happens to him. Right? Cool. That's entanglement is all about, right? Now, what if let's say there are two qubits and one is at one end of galaxy and one more is at other end of galaxy. Let's say I'm changing something here. It should also change there, right? It should also change there. Thus, the change will be faster. Thus, the change will be faster. It's a really, really high imaginary case. Hypothetical. It has to change, right? It doesn't matter what distance or what speed it is, it has to change. But technically, speed of light won't be in the case. Because when we deal with quantum entanglement, let's say we had a couple of experiments at Rama Research. There we were dealing with beam light and everything. There's huge passage of beam light. During the passage itself, there are lots of heat reducing. Like heat is lost there. Technically, I would say we can't achieve speed of light. And it's not really possible because even in the vacuum, it's not possible. Because we say in vacuum, the loss can be controlled at some extent again, but it's typically hard. Maybe hard for now. Maybe we should see a couple of generations. I mean, we are less than one generation. There are 0.7 generation. When we see a fourth generation or something, maybe it might happen some case, but it's hypothetical again. So, any other question? So there's a quick listing, and people can actually scan and give me a feedback as well. And one more, it's, and you can also follow me in LinkedIn as well. It's Panina BJ Panina. You follow there in LinkedIn. And thank you so much. Sure. What details you need? Right. Sure.
Interactive session, great session, and I appreciate consent and thank you for accepting our invitation and being part of the session. I will just Dr. Joseph, I think President Menju has been very safely, so that we can continue. So,
Driver for all of you.
yeah,
No, the not being switched. That is good.
And you realize to my engineers and comfort of companies because of meetings. It's your everything.
Without you bring their drivers. Without us. Okay, the SAGAR.